It's 8:45.
Okay.
Dr. Govind is also there.
Is there? Okay.
Good evening.
Yeah, thank you. Good morning, everybody.
Okay, so I'm starting then. Okay, so a very good morning, all of you, and very warm welcome to all of you to the NSM Computer Architecture Winter School 2021. My name is Vishwesh Jatala. I'm an assistant professor at IIT Bhilai. I'm one of the organizing member of this winter school. Today, I'm here to briefly introduce our winter school and give some details about it. So today's world is driven by the revolutions in computer technologies. Computer technology has made incredible progress over since several decades. So we started out with single core processors, and then after several decades, then we have multi-core processors, and then accelerators and application-specific integrated circuits, so on and so forth. And the research has been evolving to produce better architectures and improve performance and energy efficiency, so on and so forth. So the goal of this winter school is to create a platform where we bring in some of the eminent speakers to discuss some of the fundamental concepts in computer architectures, also introduce advanced concepts and research trends and best practices, also give a practical exposures through lab sessions to all the interested community in the computer architecture. So with this motivation, we invited several speakers from various academic institutions as well as industry, and we are thankful to all of them for agreeing to offer few lectures or lab sessions for conducting this event. And we also would like to thank all the participants for showing their interest in attending the schools. And we would like to thank the organizing members, Professor Madhura Punnaprajna from PS University, and Professor Rupesh Nazre from IC Bangalore, and Professor R. Govindarajan, IIT Madras, for the throughout supports from starting from initializing the idea till materializing the concept, including identifying the speakers, preparing the schedule, and then shortlisting the candidates, and then finally arranging the logistics. So we would like to thank all the organizing members for their continuous support on this. Also, we'd like to thank some of the lab TAs who will be helping us in the lab sessions throughout the winter school. And we are also grateful to web TAs who have helped us in setting up the website for this particular winter school. And also PS University would like to thank for hosting this particular event online and providing all the supports and logistics to conduct this event virtually very smoothly. And we are also thankful to NSM Nodal Centers for Training in HPC and AI at IIT Madras for sponsoring this event and also providing us support for the publicity and also various other activities for the organizing this particular event. So these are some of the statistics with respect to the applications. So we have received 289 applications for this winter school, and we wanted to be very selective in admitting the candidates who have specific interest in this winter school. So we processed these applications in 2 rounds. After first round, based on the credentials, we have shortlisted 224 candidates. And then for the second round, we gave some simple exercise for setting up some frameworks, etc. So based on the response we have received, we have selected 111 candidates to participate in the winter school. And we congratulate all the participants for making this to this particular event. Now moving towards the winter school, so we have prepared a nice schedule, a comprehensive schedule spanning across 2 weeks. The first week will mainly the focus will be on covering some of the basic concepts, including the lab sessions to get some practical exposures. And in the week 2, we'll cover advanced concepts with related research topics and trends in the computer architecture field. So we have sessions, various sessions. So first is the lecture session. Lecture sessions are 1 hour 15 minutes, and we also have lab sessions on each day. That is about 1 hour for 30 minutes. Apart from these 2 sessions, on each day we also have a doubt clearing sessions for 30 minutes. Basically those speakers who have taught some of the lectures or lab sessions will be there on that doubt clearing session. So please attend them and clear your doubts and concepts if you have anything need some clarity. And whole the winter school will be organized virtually through the online platform, Microsoft Team platform. So this is a brief schedule for the week 1. So this is a basic concept that will be covered in computer architectures. On the first day, we have speakers Professor Arka Prabha Brasu and R. Govindarajan and Ashish P. Kuvelkar. They'll be covering single core processor architectures. On the second day, we'll have the caches and virtual memory by Professor Arka Prabha Vasu and Biswabandhan Panda. And third day, we'll cover DRAMs by Professor Madhu Mutyam and Sparsh Mittal and Vivek Sheshadri. On the fourth day, we'll talk about energy efficiency and performance analysis by Professor Preetharanjan Panda and Subramanian KV. On the last day, we'll have parallel architecture by Professor Preeti Malakar and myself. So the fifth, the last day of this particular week 1 schedule will be a transition to the next week. So to give some of the advanced topics. On the week 2, we'll cover multi-core processor, that's by Professor R. Govindarajan and Madhu Mutyam and Arka Prabha Vasu. And on the second day of the week 2, we'll have heterogeneous architecture like GPUs and FPGA that will be covered by myself and Professor Sparsh Mittal and Madhura Purnaprajna. On third day of the week 2, we'll have RISC-V architectures. This will be covered by Professor V. Kamkoti and Neil Gala. On the fourth day, Professor Jaisi as well as Manu and Vipin will talk about advanced processor and memory technologies. On the fifth day, we'll have 4 speakers, Dr. Kanishka and then Professor Preetharanjan Panda and Subramanian KV and Vipin. They'll talk about performance and energy efficiency. So this is an overview about the schedule, but the complete schedule, including the subtopics that will be covered on each day, has been posted at the website. Please go to the website to know the details about the complete schedule. So apart from the lecture sessions, we also have lab sessions in the winter school to give a practical exposure to the computer architecture field. So these sessions are actually 1.5 hours. They are in the second half. So the speakers or the lab TAs will be helping you will help you or give you instructions to set up simulators or any tools or technologies, and they also give you demos and they float some exercises or assignments. If you have any questions or concerns, the speakers or the respective lab TAs will be available for you to clear your doubts or anything. And apart from the lab session, we also have a panel discussion, which is an interactive. This happens on the last day of the winter school from 4 to 5 p.m., where some of the speakers will discuss in an interactive manner some of the future aspects of computer architectures in terms of teaching as well as research. Also, they talk about latest trends in the computer architecture research, and the industry aspects will be discussed and career opportunities. So please make use of this particular session to get some more insights into computer architecture field. So these are some of the logistics with respect to attending the winter school. So the whole event will be conducted online through the Microsoft Teams virtual platform. We'll have all the lectures delivered there. Also, the lab sessions will be conducted. If there are any reference material, that will be uploaded into the Microsoft Teams itself. If you have any discussions or you require any doubts, everything will be conducted through the Microsoft Teams. I hope all of you must have got the login and credential details to access this particular Microsoft Teams. With this, I would like to thank you once again, all of you, for attending this particular event and showing the interest. I think now we are ready to start our technical sessions, the first technical session.
Vishwesh, are we going to be recording the sessions?
Yes. Madhura, are you there?
Yeah, the recording has started, sir. Is that okay?
Yeah, sure. No, I just wanted to make sure. Yeah, I did notice that now. Sorry, I didn't notice it. Yeah.
It has started, so I think it's a good point. Sessions will be recorded and will be available in the same environment where you're currently. You should be able to see the recording available for each lecture. If you have missed, you can always go back and look at it for the students. It's there in this environment only. If you go to the chat, you will see the recordings.
And it would make sense to record individual lectures as separate recordings.
Yes,
So,
yes, yes.
yeah, yeah.
Yeah, it will be, yeah, we are doing that. We'll break the recording now and restart.
No, this one is fine because you can continue. I'm just saying that instead of having the recording for the entire day or,
Yes,
it
yes.
would make sense to do that. That's essentially what I meant.
Yeah. Yes, sir.
So should I get started or I'm ready?
Just 1 minute of pause. Any questions from students, or is there anything before we get started? All right. A general comment, sir. I think many of the students wrote back saying that they have exams in the first week and stuff. So maybe you will not see a lot of them online, but they will be going back and viewing your lectures
Sure.
at some point. So if there are no questions, we are welcome to start.
I'll stop sharing.
Dr. Govindarajan needs no introduction. Vishwesh, you want to go ahead?
No, you can actually. I'm done. I'll stop sharing.
I think that's a good introduction, Mudra. With that, we can possibly start.
No, I think just a little bit for the students. Dr. Govindarajan is a senior professor at IISc, and he has been a mentor to this program as well as the first version earlier and a couple of other versions before too, to the Computer Architecture Winter School. He is in the Department of Computer Science and Automation and also at the Supercomputing Education and Research Center at IISc. He is, I mean, a lot of us have worked with him. He has mentored many of us and is very apt for the topics today that he's going to present. We are all eager to hear from you, sir.
Thank you. Let me start sharing my slides and then let me know if you're able to see that. You able to see my slides?
Yeah.
Yes, sir.
Okay. So, good morning, everyone. It's my pleasure to give this first lecture on this workshop. I thank Madhura and Vishwesh for organizing this and also requesting and giving me the opportunity to talk to all of you. My name is Govindarajan, as I was introduced. What we are going to see in the next 2.5 hours is some very basic introduction to processor architecture, right? The overview of my talk, the two talks that I'm going to have today, is roughly this. We'll start with a simple introduction and then talk about instruction set architecture. Then we will talk about processor data part, and then from that get to pipelining. Then we will talk about pipeline hazards and then talk about branch prediction and various branch prediction techniques. And that will lead us to out-of-order issue processors and how to do out-of-order issue. We'll talk about that. And that should set a good context for the superscalar architecture, which will be taught by Professor Kapava Basu later today. Right? So this is going to be the overview of my talk. I hope you are able to hear me well. No issues? Right?
Yes, sir.
Yes,
You're
sir, we can
clearly.
hear you.
Sure. Okay. So if you have questions, one thing you can do is that you can unmute yourself and ask me, or type the question in the chat box. But I will try to come back to that at the end of the lecture. If you raise your hand, I won't be able to see because I have put full screen on my laptop. So I would focus on the lecture. So if you have questions, maybe you wait when when I give you a pause in between, or when I ask you to ask for questions, right? Okay. So with that, we will get started. Um, First, let me just start off with this simple thing about the computer organization, the basics of computer organization. As we know, a computer system consists of the central processing unit, memory, and input-output devices. And all of this is connected by means of one or more buses, which is nothing but a set of wires. And within the central processing unit, we have the arithmetic and logic unit, which is the one which performs all the operations. Then we have a set of registers, and these registers could either be general purpose registers like the integer registers and floating point registers, which are meant for storing values temporarily, or they could be special purpose registers like program counter or instruction register, which are used for a specific purpose. The control unit in the central processing unit is the one which provides the necessary control signals to the processor or to the ALU registers as well as to the memory system. In today's computer, in addition to these components, we also have a memory management unit and multiple levels of caches. Caches are nothing but memory which is available within the processor, which provides, you can say, fast memory to access certain sets of data to the processor. Memory management unit is used for address translation. We will talk about this more in detail in tomorrow's lecture. I think Professor Arkaprabha Basu will talk about that. Right? So the processor that you see essentially consists of the arithmetic logic unit, registers, control, caches, and memory management unit. Right? Memory is the place where the program and data are stored. So when the program is executed, it is actually fetched from the memory and the instructions are being executed. And the data is accessed from the memory and written back into the memory. I/O devices are meant for doing input-output organization. Okay, now let's talk a little bit more about the memory. Some of this might appear to be very basic, but we just wanted to make sure that we all understand the terminology correctly. So let me go through this quickly. Right, as I mentioned earlier, main memory holds the instruction and data. And memory is nothing but a sequence of locations in which data is stored. And each location is uniquely identified by a memory address. Right? If each location stores 1 byte of information, then we call that memory as byte addressable. And this is the minimum unit of data that you can modify in the memory. Right? So if each location consists of 1 byte or 8 bits, then the minimum that you can write is in terms of 1 byte, and that is the minimum quantity that you can change. Right? Okay, this is what is said in the next bullet, which is the smallest data that can be modified in the memory system. So if each location consists of only 1 byte, then how do we store things like integers which are 4 bytes or 8 bytes longer, or floating point numbers which are 4 bytes or 8 bytes longer? Then the way in which we represent these larger data items is by taking consecutive memory locations. For example, 4 consecutive bytes together form one word, which might represent an integer. Similarly, 8 consecutive locations could form a double precision floating point numbers, and so on. Now, when you look at these consecutive memory locations, there is a byte ordering that we talk about. Let's try to understand this using the following example. Let's assume that we have a sequence of memory locations which store the data as is shown here. The data is in the top part, and the addresses where this addresses where this data is stored is actually shown in this blue numbers. right? For example, in memory location 400, the data 1A is being stored. 1A is basically 1 byte of information. Similarly, in location 401, right, C8 is stored, which is again 1 byte of information. Now, when we say that we want to access 4 consecutive bytes starting from 400, we're talking about the data value which are in memory location 400, 401, 402, and 403. But there are two ways to interpret this data. One is what is called the big endian, where the most significant byte, right, is in the starting location 400. Right, so in this case, we say that the 4 byte data that we are accessing is essentially 1A, C8, B2, and 46, with 1A being the most significant byte and 46 being the least significant byte. Right, this data item has a decimal value which is shown here. It is also possible to interpret this data using the little Indian format, right, where you say 46 is the most significant byte and 46B2C81A and 1A is the least significant byte. In this case, the decimal value of this number is different, right? And you can see it's almost an order of magnitude higher, right? So typically memory is just a sequence of locations where data is being stored. Which way you interpret depends on what is being implemented by the underlying systems. Some computers implement big endian format. Some other computers might implement little endian format. It should be possible for you to write a simple C program to understand whether your laptop or your computer system supports big endian or little endian. Okay, next we will try to clear certain terminology with regard to word size and word alignment, right? So word size typically represents the largest data that can be obtained in a single fetch from the memory. Or you can also say this is the largest data that can be modified in the processor, right? Typically this would be something like 4 bytes, which essentially means in a single fetch from the memory, 4 bytes of data can be accessed, right? And a word alignment refers to whether the word that we are talking about starts at a location, right, which is aligned for the word. So since word is 4 bytes, we say word boundaries are typically multiples of 4. So if the address is a multiple of 4, then we say that the word is word aligned. If it is not a multiple of 4, we say it is not word aligned. Typically instructions, right, are word aligned in a RISC processor, right? For a RISC processor, the instructions of a program are always stored in a word aligned fashion. That means that they will all be in addresses which are divisible by 4. Okay, so that's a very quick introduction to the organization of the computer system. Let's look at instruction set architecture next. Okay, before I go there, I just want to make sure that all of you are able to hear me well and also able to see the slides as well as my cursor pointer. Are there any issues?
No, sir, we can hear you. Yes, sir, clear.
It's clear, sir.
Okay, good, thank you. So I suppose there should be no questions because whatever we have seen so far are just some basics, and we will get started now. Okay, so when we talk about instruction set architecture is basically the view of the computer visible to the programmer or to the compiler, right? And there are two kinds of instruction set architecture that we talk about. Most of you would have heard about this. One called the complex instruction set computer or CISC-ISA. The other one is called the RISC-ISA or the reduced instruction set computer. In a complex instruction set computer, the instructions are such that they can perform complex operations in a single instruction. Whereas in the case of a reduced instruction set computer, each instruction performs only a simple operation, but it is able to perform this operation, right, fairly fast, so that you could get a good execution speed, or you could complete the execution of the program faster. May I request all of you to mute your microphone if you're not talking, so that there won't be any disturbance for the others. Thank you. So in this lecture, we will discuss about the reduced instruction set computer and the instructions in a reduced instruction set computer. And we will briefly talk about what would be the complexity or what would be the issues for supporting a complex instruction set computer. We will not get into too much of discussions on this, but basically talk about a few important issues that separates these two approaches. Okay, so when we talk about the instruction set architecture, as I mentioned, it is a description of the machine from the view of the programmer of the compiler. For example, if you say the x86 instruction set architecture or the MIPS instruction set architecture, right? That tells you what is the instruction set architecture which is understood by the particular processor. The instruction set architecture itself consists of three things. One is the set of instructions, which is what we will talk about. The other one is the addressing mode, which essentially specifies how the operands for different instructions are specified, how the operands for an instruction are specified. That's the addressing mode. The third, which is a less important thing, is about the instruction format, which essentially tells how the instruction is encoded in terms of bits, right? In each one of these aspects, the CISC and RISC ISAs differ. We will also point that out as we talk about the instruction set or the addressing modes and so on. Okay, now when you talk about the instructions, there are different types of instructions that we talk about. Right? There are these instructions which are arithmetic and logic instructions which perform an arithmetic or a logic operation, such as the integer add, subtract, multiply, or the floating point add, subtract, multiply, compare operations. Or you can do the logical operations such as logical OR, and NOT, or XOR. Or you can also talk about, either logical shift or arithmetic shifts, right? You can talk about them. You can talk about the rotate operations and so on. All of these operations are called arithmetic or logic operations, right? And these are typically performed by the arithmetic and logic unit inside the processor. There are also data transfer instructions that we talk about. And typically these data transfer instructions are essentially to move data either from memory to a register or from the register to a memory location. Or you can also do move operations, which is from one memory location to another memory location. Right? Then we have the control transfer instructions, which are essentially conditional branches and jumps or unconditional branches in your program. We also include things like function calls and returns, which also transfer program control from one point in program to another point. Lastly, we have also other instructions such as halt or trap and other things and so on. If you look at a RISC machine, a RISC machine supports arithmetic and logic instructions. It also supports data transfer instructions, but these data transfer instructions are typically restricted to load to a register or store from a register to memory. They typically do not have a move instruction where you move from one memory location to another memory location. And also in a RISC instruction set architecture, the arithmetic and logic instructions have their operands always in a register or as an immediate constant. And only load store instructions would have memory operands. This is what that distinguishes the RISC instruction sets from the CISC instruction set. Whereas in the CISC instructions, you could have arithmetic and logic operations having one or maybe even two memory operands, right? You could have data transfer instructions moving data from one memory location to another memory location, and so on. Right? Next, we will talk about the different addressing modes which are supported. Right? Addressing modes essentially is how an operand is specified in an instruction. Of course, when we talk about operands, there could be source operands in an instruction as well as destination operand, right? And the addressing modes essentially talk about what is the location of these operands, right? And the operand can be either in memory or in a register. We will see how these operands can be specified using a set of addressing modes in the following slides. But before we go that, your instruction set itself can have instructions which will either have 3 operands or it will always have 2 operands, at most 2 operands or at most 3 operands. There are also instructions which have 4 operands, right, where you have 3 source operands and 1 destination operand. Typically, when we talk about a RISC machine, we talk about a 3-address format, which is something like this, where you have add R1, R2, R3. In comparison, in a 2-address format, you have a subtract instruction with 2 operands. One of them is both the source and the destination, and the another one is just a source. For example, in this case, it could be the thing that R1 is both a source operand as well as a destination operand, and the second source operand is A, right? Whereas in the case of a 3-address instruction, one of them is the destination operand and the other 2 are source operands. Okay, now we will see the different addressing modes which are supported. The simplest addressing mode is the register direct addressing mode, in which the operands are available in the general purpose registers inside the processor, right? So for example, here you talk about an add instruction with 2 source operands R2 and R3 and a destination operand which is R1, right? And the meaning of this instruction is that the contents of R2 and R3 are added and written into R1. This is illustrated in this simple animation that you can see. If the contents are 24 and 35 in R2 and R3, then after the addition, the content would be 59 in the R1 register. The second addressing format is what is called the immediate addressing mode, in which the operand is specified as a part of the instruction. For example, it would be a small constant which would be specified as a part of the instruction. Oftentimes, we would like to add 1 or 4 or 8 or 16 or maybe even a negative value like -8 and so on, and they are specified as a part of the instruction itself, as you can see over here, right? And in this particular case, what happens is that one of the source operand is the contents of the R2 register, and the other operand is a constant 1, which is obtained from the instruction. The third addressing mode is what is called the register indirect addressing mode, in which the operand is available in the memory and the location from where you have to access that operand is specified in a register. So this is called the indirect addressing mode. People who have used C program, they know about pointers. So you can just think of R2 being a pointer to the memory location. So in this case, again, this animation would show you what's really happening here. If you have a sequence of memory locations, right, and let's say their addresses from starting from 96 onwards, I have just for the purpose of simplicity, I have used all the addresses to be decimal, but of course, all of this is going to be represented in the computer as a hexadecimal thing. So, I mean, it's easy to think about it that way, right? So for example, when you have a move instruction which uses the operand as R2 indirect addressing mode, then this specifies that you have to access the memory location whose address is in R2. Since R2 contains 100, you access the memory location 100, and the value which is stored in that memory location, which is 10, right, is what is going to be moved into the destination register, which is R1, and therefore after executing this instruction, R1 gets 10. Now, if you look at the base displacement addressing mode, which is an extension of the register indirect addressing mode, this is also an indirect addressing mode But in addition to the register having a pointer to the location, a small offset, in this case 4, is added to the address, right? And that is what is used as the address of the operand. So again, a same example, right? And here, because the offset is 4, we add 4 to 100 and take the value which is from memory location 104 and store it in the destination register R1. The calculation of R2 plus 4, right, which is what is called the effective memory address, right, is done by the processor, and after that the memory is accessed and that value is being written in R1 register. Okay, so again, if you look at the RISC instruction set architecture, they would support the register direct addressing mode, they would support the immediate addressing mode, and they would support the base displacement addressing mode. The register indirect addressing mode is nothing but the base displacement addressing mode with offset 0. Right? So in some sense, that is also included if the offset is 0. We will also talk about some more complex addressing modes, which are typically only supported in the CISC instruction set architecture, but not in the RISC instruction set architecture. So I will go through them somewhat quickly so that we can complete our discussion there. Okay, the fifth addressing mode is what is called the absolute addressing mode. Here again, the operand is in the memory, but the address of that memory location is directly specified in the instruction. So for example, here we say that add R1, R2, and then the address 100, right? So the contents of the memory location 100 is accessed, which is added to the contents of R2, and the result is being stored in R1. And the memory location's address is explicitly specified as a part of the instruction. Since the memory address can be 32 bits, this instruction to specify the absolute address would typically require more than 4 bytes of information, right? There is another addressing mode called the indexed addressing mode, where the address, where again the operand is available in the memory, but the address of the memory location is being specified as a combination of 2 registers, R3 and R4. Right? So if you add the contents of R3 and R4, the value that you obtained is the effective memory address, then that particular memory location is fetched as the operand. We also have something called the auto increment or the auto decrement addressing mode, where again the operand is in memory and the address of the memory location is specified by means of a register. But in this case, what happens is that the contents of this register, in this case R3, is either incremented or decremented depending on whether it is an auto increment or an auto decrement addressing mode. And of course, this increment or decrement happens either after the access or before the access. So it's always called post increment or pre-decrement addressing modes. These addressing modes are useful if you want to access the locations, let's say, of an array. So after accessing the location, the address is automatically incremented or the address is automatically decremented so that you can access the next location in the array. Again, these addressing modes are typically supported only in a CISC instruction set architecture. You also have something called the PC relative addressing mode, where the program counter is used as the index register and an offset from the program counter is specified as a part of the instruction, and that location is being accessed. Typically, small constants which you want to store as a part of the program are stored in what is called the PC relative addressing, is stored and then is accessed using the PC relative addressing modes. Again, we will not worry about all of these addressing modes. We'll probably focus on the first 4 addressing modes, which are what are going to be supported in a RISC architecture. Okay, so far what we have seen is that we have seen the instruction sets in a RISC machine. We have also seen the different addressing modes which are supported. Now let's look at the MIPS instruction set architecture as a case study. The MIPS instruction set architecture, or the MIPS processor to start with, and its instruction set architecture essentially consists of 32 general purpose registers. In fact, it has 32 integer registers and 32 floating point registers. Each one of them is 32 bits, right? And in the case of the MIPS register R0, right? And so of course these registers are called R0 to R31 for integer registers and F0 to F31 for floating point registers, right? And the R0 register will always have its value as 0. It is hardwired to 0, and this is used for various purposes. And R31 is implicitly used as the link register, okay, in implementing subroutines, which are typically implemented using the jump and link instruction or the jump and link register instruction. Of course, there are two other registers which are called high and low, right, which is typically, each one of them is 32 bits, and this is used for multiply and divide, because when you multiply two numbers 32 bits each, you will get a 64-bit number, and they are stored in the high and low register respectively. Okay. The addressing modes that are supported in the MIPS ISA are the immediate addressing mode, where the operand is specified as a part of the instruction, or the register direct addressing mode, where the operand is in the register. It also has a base displacement addressing mode, which is used in load store instructions, right? And the PC relative and absolute modes are only used in jump instructions and branch instructions respectively. Branches are typically PC relative, and jump instruction is absolute, where you specify the location to which the jump has to take place. We will see examples of these different instructions and how they use the different addressing modes. Okay, now let's look at the MIPS instruction set and the various instructions that are available in the MIPS architecture. First, we will look at the load store instructions. The load store instructions, the load instruction is to move a data item from a memory location to the register. So an example of a load instruction is the load word instruction that you see here, which loads 4 bytes of data from a memory location whose address is specified as R3+4, and the data value is moved to the destination register R2. So you can see that the memory location at the address R3+4 is moved to R2 register, right? The different load instructions are: you can load a byte, you can load a half word, which is 2 bytes, or you can load a word which is 4 bytes. And the U here stands for the unsigned. So when you load a word, when you load a byte or a half word, right, you are essentially loading only 8 bits or 16 bits. And if you sign extend them using the 0 bits, right, that is called unsigned. You are treating them as unsigned, right? That's what is the suffix U there stands for. Similarly, we have a store byte, store half word, and a store word instruction also, right? The move instructions are to move the high and low register that I talked about in the previous slide to a specific general purpose register. For example, if you want to move the H1 register to R1, then you say move, right, from high register to R1. If you want to move some contents of R1 into high register, then of course you say move to high register from R1, and so on. We also have a set of arithmetic and logic instructions, and arithmetic and logic instructions use only register operands. And as you can see in all of these examples, all the operands are either register operands or immediate constants. For example, here there is a shift right instruction, right, where one of the operands is specified as an immediate constant. You could also have an add or a subtract instruction where one of the source operand is specified as an immediate constant. Of course, there are examples for multiply, divide, and so on. I'm not going to go into each one of them, but if you go through that, it's fairly easy to understand what they do. I have also defined the meaning of each of these instructions in the last column. The last set of instructions are the branch instructions. Okay. So there are conditional branch instructions, like for example the branch equal instruction, branch greater than 0, branch less than 0, and so on, where the branch condition is specified as a part of the instruction, and of course the register which is tested for this condition is one of the source operands, and the location to which the control has to take or control has to go if the branch condition is true is specified by means of an offset value. This offset value is going to be added to the program counter. In fact, it's going to be added to the program counter plus 4, right? And the offset value is added to that, and that will be the new program counter if the condition is true. For example, in this case, we are talking about branch less than 0, right? If R2 has a value which is less than 0, then the program counter will be changed to program counter plus 4 minus 16, which is the offset in the instruction. So when you write your program, you typically write branch less than 0, go to a label called out or go to a label called loop, right? But then when that program is compiled or is assembled, to be more precise, the assembler identifies how far apart is that labeled instruction, and that offset value is basically encoded as a part of the instruction, right? And that offset is typically a small constant. In the case of MIPS, it can be a small constant which is represented as a 16-bit 2's complement number. Right? When I say 16-bit 2's complement number, you can see that it can go from minus 32k to plus 32k. Right? So if the location to which the control has to transfer to is plus minus 32k, then it can easily be specified as a constant, right? And the assembler actually computes this offset and puts it as a part of the instruction, so that when the instruction executes, this offset is available directly as a part of the instruction and is added to the program counter value. In fact, the program counter value plus 4 is what is called the next program counter value, to which the offset is added, and the control jumps to that location if the condition is true. If the condition is not true, of course, it will go to the next location. You also have jump and jump register instructions, right? Where the jump location, target location, is specified as a part of the instruction. This is what I called as absolute address. Here in this particular case, 26 bits of absolute location value is given as a part of the instruction. The jump and link register instruction, right, or the jump and link register instruction, jump and link instruction as well as jump and link register instructions, they are used for implementing subroutine calls, right? So when you do that, what happens is that the control jumps to the location specified in R2, right, which is basically an indirect pointer or a pointer to the location, right? And the current program counter value plus some value plus 8 is what is going to be stored in the R31 register, which is what is going to be used to jump back to this routine. Okay, so there you will use a jump register instruction to come back, which is what is called the return instruction. Okay, that is for a simple jump. If you have recursive calls, of course, you need to take care of that in a more complex way, right? There is also a system call instruction, which is called syscall. I will not go into the details of that. So this gives you an idea of how the MIPS instructions, what are the different MIPS instructions and what do they mean. Let's also very quickly look at how the MIPS instructions are encoded. Each MIPS instruction is encoded, right, as a 32-bit entity, right? And this encoding is what is called a fixed format, because the most significant 6 bits always represent an opcode. And those 6 bits essentially tell whether the instruction is in the OR format, I format, or J format. If it is in the OR format, then of course it specifies two source operands, one destination operand, and then there is something called a shift amount, which is for 5 bits, and there is an additional function specification which is for 6 bits. So in this particular case, the opcode plus these 6 bits of function together specify what is the operation to be performed. Then it has two source operand, one destination operand, and then possibly a shift amount. Right? The shift amount is only used for arithmetic and logic shift operations. If the instruction is in the I format, then it has an opcode, one source operand, and then one destination operand, right? And an immediate constant which is 16 bits. Okay. If the instruction is in the J format represents absolute address, and in this particular case the opcode is 6 bits, the remaining 26 bits are addresses, and it is kind of concatenated in a particular way to generate a 32-bit address. We will not worry about those details, right? So as you can see, the instruction encoding is in a fixed format and very simple. Compared to this, if you look at something like a CISC instruction encoding, is rather complex. Okay, now let's quickly compare. Okay, thought I had a slide on RISC versus CISC. Maybe that is coming up a little later. Okay, so that kind of concludes our discussions on the instruction set architecture. Let me just take 1 minute to see if there are any quick questions. If you have a question, please unmute yourself and ask.
Sir, can a particular processor be given all these 3 types of instructions, sir?
What do you mean by all the 3 types? You are talking about the instruction format?
Like, yes, sir. R type, I type, and J type.
So in the case of the MIPS MIPS processor, right? There the instructions are encoded using these 3 types. If you look at some other processor, there the encoding may be different. Maybe there are some 7 types or 6 types, right? In the case of, for example, the RISC-V instruction set, which you will probably see sometime during the 4th day of this workshop, right? They have a very different format, and they have that is also a fixed format, but it has something like 6 or 7 different types of instructions. So this 3 types is specifically for the MIPS processor.
Okay, sir.
Any other questions? Okay, let's get going. And then again, towards the end of this lecture, we will take more questions. Next, we want to talk about processor data path, right? In this particular thing, what we want to do is we want to understand how the instructions are getting executed. The instruction execution itself is going to be split into a number of stages, right? And we will see how this instruction execution can actually be implemented by the processor. So we will divide the instruction execution into instruction fetch, instruction decode and operand fetch, execute, memory, and write back stages, right? And we will talk about each one of these stages and how what exactly happens in each one of these stages. In the instruction fetch stage, the first thing that we need to do is to fetch the instruction. The instruction is pointed to by the program counter, right? We know program counter is a special register, right? And that holds the address of the next instruction to be executed. Therefore, you use that address, okay, and then access the memory. That gives you the instruction to be executed. So that value, when you access it from the memory, should go into the instruction register, which specifies what is the instruction to be executed, right? In the case of MIPS and in the case of many RISC architectures, as I mentioned earlier, since each instruction is 32 bits, which is exactly 4 bytes, the next instruction will be at a location which is 4 bytes from the current location. Therefore, the program counter is incremented by 4, and that gives you the next program counter. So both of these operations are performed in the instruction fetch phase. So that is depicted in this figure on this right hand side. So you take the contents of the program counter and you add 4 to it. That gives you the next program counter, which is the second line here. You take the contents of the program counter, use it to index into the instruction memory or memory, correct? That gives you the next instruction to be executed, and that is stored in the instruction register. So this is essentially what is done in the instruction fetch stage. Right? Next, let us look at what happens in the operand fetch. Right? Operand fetch or instruction decode and operand fetch stage. Right? So in the instruction decode and operand fetch phase, once you have the instruction in the instruction register, you try to fetch the various operands. Again, we are going to talk something which is specifically for the MIPS architecture. And again, remember that in the case of MIPS architecture, we said that the instructions are going to be either in the R format or in the I format or in the J format. And it is a fixed encoding, right, of instructions. Therefore, you can see that the source operands are always specified by certain number of bits in the instruction. Similarly, the destination operand is being specified by certain part of the instruction. If the instruction has an immediate constant, then it will always be from bit 0 to bit 15, the least significant 16 bits. If it has an absolute address, it will be the least significant 26 bits. This is all fixed in the instruction encoding, right? And even before you understand what the instruction is, you can actually start decoding the instruction and understand where the operands are going to be, right? So what is being done in the case of the MIPS processor is that in the instruction decode and operand fetch phase, right, the bits corresponding to the source registers are used, and you index into the register file to get the first source operand. Similarly, you use the bits corresponding to the second source register, index into the register file, and get the operand into another temporary register. You don't know at this point in time whether the instruction is in the R format or in the I format. But it doesn't matter because you are only doing a read from the register file, and read is not a destructive operation. So you can assume that the instruction is going to be, if the instruction is of the R format, then these bits represent the second source operands, and I will try to read one extra register and keep it in the B register, right? But if the instruction is in the I format, then the least significant 16 bits, right, are the constants, and I have to do a sign extension of them to get a 32-bit value, and I do that to get the immediate constant value. So these are done by the hardware in the following way. You take the instruction register, use the appropriate bits to index into the register file and get the value, right, which is the first source operand, and store it in the A temporary register. Use the appropriate bits for the second source operand, index into the register file, read that particular register, and store it in the B register. If the instruction is an I format instruction, then of course you will have to use the least significant 16 bits, and then you do a sign extension of that, and you get the immediate constant. So one of the, any two of this would be the operands for you to perform any operation during the execute stage or in the memory stage. We will see that in the next step. So as I mentioned here, in the instruction fetch phase, of course, you wouldn't know what the instruction is. That's because you are fetching the instruction. But even during the decode phase, you don't so much worry about what the instruction is about, whether it is an R format instruction or it's an I format instruction. You continue to read two source operands and then also try to get one immediate constant. If the instruction is R format, then you discard this immediate constant. If the instruction is I format, you discard this B register and then use the remaining operands to perform the operation. If it is a J format instruction, of course, none of this would make sense, so you discard all of them. Right? But you can actually read all of them and get it ready during the instruction decode and operand fetch phase. So as you can see here, because the instruction follows a very simple format, you can actually do this instruction decode and operand fetch even without knowing what the format is and what the operation is. Right? Okay, now let's see what happens in the execute phase. Now in the execute phase, depending on what the operation is and what format the operation is, you have to perform the operation, or the processor has to perform the operation. So let's see different examples here. If the instruction is an arithmetic instruction, then it can either be in the OR format like this. I'm sorry. Yeah, it can be in the OR format like this, or it can be in the I format like this. But irrespective of whether it is in the OR format or I format, we have already fetched the operands. One of the source operand is R2, which is available in the A register. The other source operand is either from R3 register or the immediate constant 16. Again, as we saw in the previous slide, these operands are available either in the B register or in the immediate register. And all that we need to do is to perform now this operation using either A and B register or using A and immediate register. So that is shown in this diagram by using a set of multiplexers. So these multiplexers choose the appropriate values. In this case, it will choose A and either B or immediate, depending on whether the instruction is in the OR format or I format. Then of course it will send control to the ALU to perform whatever is this operation. This operation could be an add operation, subtract operation, or a multiply operation, or some kind of a logical operation. So that control is sent to the arithmetic and logic unit, and you perform that operation, and the result value is stored in the ALU out register. Okay. Now let's see what happens if the instruction is a load store instruction. If the instruction is a load store instruction, right, then the first thing that we need to do is to compute the effective address of the memory location. Again, as we saw in the previous slide, the source operand R2's value has been loaded into the A register, and the immediate constant 16 is available in the immediate register. Therefore, all that we need to do here is to compute the effective address, which is nothing but the A register plus the immediate register. That is again performed by the ALU, and the effective address is stored in the ALU out register in case of a load store instruction. If the instruction happens to be a branch instruction, right, then we need to evaluate the branch condition as well as the branch target. As I mentioned earlier, the branch target is nothing but the next program counter value, which is essentially PC plus 4, plus the immediate constant. Right? The next program counter is already available because this was computed during the instruction fetch phase, and the immediate constant is available in the immediate register. Therefore, if you add these two things, so for example, NPC comes from here and the immediate value comes from here, and if the ALU adds up these two things, then you get the branch target address in ALU out. So as you can see, depending on whether it is an arithmetic instruction, load store instruction, or branch instruction, the ALU out will contain the result of the arithmetic operation or the effective address of the memory location to be loaded or stored, or the branch target location in the ALU out register. For the branch instruction, there is also a condition evaluation that is required. For example, let's say if the condition is equal, then you're basically checking whether, I'm sorry, actually I have used not equal here, whereas I have used equal here, but it's okay, right? So if it is a not equal condition, then you are checking whether R1 is not equal to 0, right? Or if it is an equal, then you will check whether R1 equal to 0. And then depending on that, this condition register would be set. Okay, now let's see what happens for load store instructions in the memory stage. Okay, sorry, before I go there, sorry, I forgot to mention about the jump instruction. In case of jump instruction, right, it's an unconditional jump, and the location to which you have to jump to is specified in the least significant 26 bits of the instruction. So you take those 26 bits, concatenate it with 2 bits 0, 0. This is because all instructions are 4 bytes long. Therefore, the least significant 2 digits in the address will always be 0, 0. And the most significant 4 bits would be nothing but the most significant 4 bits of NPC. That means that you are in the same segment, right? The most significant 4 bits are same as the current program counter value or the next program counter value. So you take 4 bits from the next program counter value, take the 26 bits from the instruction, as well as 2 0 bits, concatenate all of them to get the next program counter value. And that value is written into the program counter so that the next instruction that is going to be fetched will be from that location. Okay, so this is exactly what happens during the execute stage. Depending on what type of instruction it is and what format the instruction is, appropriate action is performed by the processor. Okay, now let's look at the memory phase, right? Of the instruction execution. In the memory phase for load store instructions, of course, the memory phase is applicable only for load and store instructions in the case of MIPS processor, which is a RISC architecture, right? We have already calculated the address, effective address R2 plus 16, which is available in the ALU out register. So you use that information, index into the memory, and get the value into a register called LMD. Load memory data. If it is a, okay, so that looks something like this. You take the ALU out, which gives you the address of the location, index into the data memory, and the value that you fetch is stored in the LMD register. If it is a store instruction, then the store instruction has one source operand which specifies what is the value to be written, which is available in the B register. It has another source operand which is a pointer to which you have added the immediate offset, and that value is available in the ALU out register. So you index into the memory location and you write the value of B register into that location, right? That is essentially a store operation. Store does not write anything into the LMD register. It only writes the value into the memory. Okay. Now the last stage is the write back stage. Again, in the write back stage, depending on what the operation is, appropriate action is performed. If it is an arithmetic and logic instruction, then we know that the ALU out register contains the result of the arithmetic and logic operation. So that is now written in the destination register in the register file. So ALU out is being written into the destination register. If it is a load instruction, then the loaded value is available in the LMD register, which now has to be copied into the destination location or the destination register. If it is a store instruction, the value is already written into the memory, so nothing is performed in the case of the write back stage. If it is a conditional branch instruction, if the condition is true, then the ALU out, which is the target PC location to which the branch has to go to, that value is stored back into the program counter. If the condition is false, then of course you will go to the next program counter, which is nothing but PC plus 4. So that value is copied into the program counter. So if the condition is true, you get the target location into the program counter. If the condition is false, you go to the next program counter. So that implements conditional branch. We already saw that in the case of jump instruction, right, the program counter is updated with the jump address that we have got. Now putting all these things together, you get the processor data path in the following way. So you have the instruction fetch phase where you fetch the instruction as well as increment the program counter. Then you index into the register file, get the AB operands as well as you do sign extension. Then in the execute stage, you perform either the ALU operation or you compute the effective address of the memory location for load store instruction, or you compute the target address for branch instruction. For branch instructions, you also evaluate the condition. Then for the load instruction, you load the value from memory into the LMD register in the memory state. For store instruction, you write the value of B register into the location which is pointed by the effective address, which is computed in the ALU out register. Right? And of course, in the write back stage, right, if it is a load instruction, you take the LMD value and write into the destination register. If it is an ALU instruction, you take the ALU value which comes through this multiplexer and write into the destination register. If it is a conditional branch instruction, then if the condition is true, right, then you choose the target location and write into the program counter. If the condition is false, right, then you take the next program counter value and write into the program counter. I have not shown what happens in the case of a jump instruction here. Okay, so that essentially summarizes the processor data path. Okay, let me complete 2 more slides and then give a gap for questions. Okay, so again, the same processor data path that is drawn here. Now, let's assume that each one of these stages that we have talked about, right, say that same amount of time, right, then that could be described as the processor cycle time, right? For example, if you say that I have a processor clock like this, and say instruction fetch can be completed in 1 cycle, or instruction decode can be completed in 1 cycle, and so on, then each one of these stages is completed in 1 cycle. So if an instruction goes through all of these 5 stages, it will take 5 cycles to complete. For example, the load instruction, which goes through all these 5 stages, would take 5 cycles to complete. Whereas the arithmetic instruction or the store instruction goes through only 4 of those stages, and they may take only 4 cycles to complete. Right? But in order for me to do this, I have to make sure that all the operations that are performed in any one of the stages can be completed within this cycle time. So this is how the processor cycle time is being determined. Once you divide them in terms of stages, all the operations which are performed within that stage has to be completed within 1 cycle. Right? Whether it is the instruction decode stage or the execute stage or the memory stage or the instruction fetch stage, whatever are the operations which are performed within the stage, all of them have to be completed within this cycle time. If it is so, then of course you can, right, you can perform these different operations in 1 cycle each, and you can, this is actually important, more important for pipelined processors, because in pipelined processors, these different stages are going to be overlapped, as we will see later, right? So this is very important that each one of these stages has more or less the same amount of time, and the slowest stage essentially determines what is the cycle time. Okay. Of course, here we are making a lot of assumptions saying that the memory can be accessed in a single cycle, these operations can be performed in a single cycle, and so on. Later on, we will relax these right assumptions and then say what happens if it takes more time, or how do we make sure that the memory can be accessed in 1 cycle, whether we can use caches and so on and so forth. Okay, so let me talk a little bit about the performance of processors, right? As I mentioned earlier, if each stage, right, of the processor takes 1 cycle, then all the actions in that stage must be completed within that 1 cycle. And smaller the stage, the faster is the access time, or the smaller the cycle time, faster is the clock rate. Right? For example, you know that when we talk about processors, we talk about something like 2 gigahertz cycle, or we talk about processor operating at 2.5 gigahertz or 3.2 gigahertz and so on. Right? If it is a 2 gigahertz processor, then the cycle time is 0.5 nanoseconds. If it is a 4 gigahertz processor, then the cycle time is 0.25 nanoseconds and so on. Okay. And different types of instructions take different number of cycles to complete. And we already saw that in the case of this processor, arithmetic instructions take 4 cycles, store and conditionals also take 4 cycles, whereas load takes 5 cycles and jump takes 3 cycles. Now, given that these different types of instructions take this much amount of computation time or this much amount of cycles to complete their execution, right? What would happen to a program which has, let us say, 40% of the instructions as arithmetic instructions, 10% of the instructions as store, 20% of the instructions as conditional instructions, another 20% of the instructions as load instructions, and another 10% as jump instructions. Then if I have a program with that kind of an instruction mix, then the average number of cycles taken for executing an instruction in that program with that given instruction mix can be calculated as the weighted sum, like what is shown here. So you take 40% of the instruction, which is 0.4, multiplied by 4 cycles for arithmetic instruction. 10% of store instruction, which is 0.1 multiplied by 4, and so on. So if you compute all of them, you get something like 4.1 cycles. Okay, now to compute the execution time of the program, you essentially multiply the cycles per instructions with the instruction count, that is the number of instructions which are executed in the program. This will give you the total number of cycles. In order for you to compute the execution time, you have to multiply it by the cycle time. Right? If it is a 2 gigahertz processor, then the cycle time is 0.5 nanoseconds. And one important point to remember here, when we say instruction count, we are talking about the dynamic instruction count, right? The number of instructions which are executed. It's not the number of instructions which are in the program, right? Because you know that if you have a loop and there are, let's say, 10 instructions in the loop and the loop is iterated 100 times, then of course just for the loop, right? 100 into 10,000 instructions will be executed. So the dynamic instruction count of the instructions within the loop is 1000, whereas the static instruction count is 10. So we're going to distinguish between the static instruction count and dynamic instruction count. And in computing things like the execution time, it is the dynamic instruction count that is important, right? Okay. Now let's quickly look at the difference between the CISC instructions and the RISC instruction execution. Right? In the case of CISC instructions, the instruction size is, in the case of RISC instruction, the instruction size is fixed, whereas in the case of CISC instruction, the size varies. Therefore, you could have to do multiple instruction fetches. CISC instructions also have a non-fixed instruction encoding format. Therefore, decoding is complex and may take multiple cycles. The arithmetic instructions may have memory operands, therefore it would involve memory access, and which means that it would involve address calculation in the first place, which all could complicate the matter. The instructions itself could contain block move instructions, which may take variable amount of latencies, and in case there is an exception which is raised in between, that causes additional complications. Of course, the actions in a single stage themselves are complex, therefore cycle times are longer, and the control logic is also complex. Okay, I'm going to leave these discussions about CISC versus RISC only to this, and I don't want to encourage any debate on that at this point in time. Later on, when you talk about the x86 architecture, x86 is essentially a CISC instruction set architecture, but is implemented using what are called the micro ops, which are RISC instructions, right? So when Professor Arkaprabha Basu talks about superscalar processors, he will be alluding to this as micro ops and things like that. Okay, so let's leave the discussions there and then move on to the next part of the discussion, which is pipelining. But before I get into pipelining, if there are any questions on the processor data path, I can quickly take that. Any questions? Are we doing okay? Be able to understand so far?
Yes, sir.
Yes. Yes. Yes, sir.
Yes, sir. Yes, sir.
Sir, one doubt I have is why are you saying that each part of the stage of the instruction should be completed within one cycle, sir? Like the instruction fetch, instruction decode. Why should it take only one clock cycle?
If it takes more cycles, in the case of a non-pipeline processor, it wouldn't be a problem. Okay. So for example, let us say execution takes 3 cycles instead of 1 cycle. It doesn't matter. Yes, no problem. Right, arithmetic instructions instead of taking 4 cycles may take 6 cycles. Load instructions may take 7 cycles and so on. That should not be an issue in the case of a non-pipeline processor. But when it comes to a pipeline processor, we are going to overlap their executions, as you will see in the very next slide. And if the stages are going to take different amount of time, then pipelining is going to be done using the slowest stage. So if, let's say, execution takes 3 cycles rather than 1 cycle, then the pipelining speed itself is going to be every 3 cycles is what you are going to call as one pipeline stage. So whether it is instruction fetch or decode or execute, everything will take 3 cycles in that case. All right? You will see that right in the next slide. Okay?
Sir, one more question.
Sure, quick.
Sir, in supercomputer, is it RISC or RISC?
It depends on the processor. It depends on the processor, right? If I have a MIPS processor, it is a RISC processor. If I have
it has nothing to do with supercomputers or simple computers.
Yeah.
Okay, sir. Thank you.
Okay, a supercomputer could have a combination of systems, right? It could have CPUs, GPUs, FPGAs, and so on and so forth. I have complicated the question for you without answering, right? That's okay. Okay, let's look at pipelining. So what we have seen so far is that instruction execution, right, in the case of a RISC instruction consisting of 5 stages, right? You could do one thing, execute each instruction one at a time, complete all the stages, and then start the next instruction, in which case each instruction would take, let's say, assuming every instruction takes 5 cycles, then of course it will take 5 cycles followed by another 5 cycles followed by another 5 cycles and so on. But it doesn't make sense to wait for all the stages to be complete before you start the next instruction. In fact, you could overlap their execution in the following way. When the ith instruction goes to the instruction decode stage, the i+1th instruction can be started in the instruction fetch stage. Similarly, when the i+1th instruction goes to the instruction decode stage, the i+2 instruction can be fetched. And of course, all the previous instructions go to the next stage and so on. So if you try to do this, and if all these stages take exactly the same amount of time, this is why it is important that they all take the same amount of time, right? You could see that you could nicely overlap the different stages of the pipeline. And when you do that, what happens is that even though each instruction takes exactly 5 stages or 5 cycles to complete, right, you could see that after the pipeline is filled, right, in every cycle you get a new instruction completed. Therefore, what happens is that even though the instruction latency is 5 cycles, the throughput is 1 cycle per instruction, because in every cycle you could get 1 instruction completed, right? That essentially improves your CPI from something like 4 or 4.1 down to just 1, right? Okay, so there is an initial pipeline fill time which is exactly equal to the number of stages minus 1, and then after that you will get 1 instruction completed in every cycle. Of course, this happens only in the case of an ideal pipeline, right? We will see what happens when the pipeline is not ideal or what are the issues involved right in the next few slides. But before that, we will see how do I implement this pipelined execution of processor. What we saw in the earlier diagram was just the processor data path without taking into consideration pipelining. Okay, so it's the same diagram that we saw earlier with some small changes, right? what are the changes that you see? You see that there is a big buffer between every successive stage, right? There is a buffer between the instruction fetch and decode stage. There is another buffer between the decode and execute stage. There is a buffer between the instruction memory stage and so on. What this buffer consists of is essentially a set of registers. This set of registers copy certain values. For example, a very simple example is that once the instruction is fetched, it is there in the instruction register. When you are executing the instructions in a non-pipelined manner, there is only one instruction that we are talking about, and that can be in the instruction register. And you can always refer to it to find out what is the source operand, right? Register number, what is the destination operand's register number, and so on. But like what I said in the previous slide, if you keep fetching one new instruction every cycle, right? By the time that the ith instruction goes to the write back stage, right, there will be 3 or 4 other instructions which are fetched and which will be overwriting into the instruction register. How do I find out what is the destination register for my ith instruction? Correct, that information would have been lost if I have not been careful, or if the processor has not implemented something specifically for that. So that is taken care of by just having one IR register in each one of these buffers. So as the instruction travels from one stage to the other, that IR value is copied from one buffer to the other. Therefore, when the ith instruction goes to the write back stage, the IR register which is over here, right, is the one which is going to hold the destination register value for the instruction which has to do the write back, right? Similarly, when, let us say, some I plus third instruction is in the instruction decode and operand fetch stage, the IR register which is over here, which will be holding the instruction for that particular instruction, right, which is in the decode stage, and that will specify all the source operands where they are, and you can actually index it from there. Not only that, we talked about the ALU out register, right, which will be over here, which is actually copied into this particular buffer. And later on, when the ith instruction moves to the write back stage, that same ALU out value would be copied from here to here. So that when the ith instruction, which is an arithmetic instruction, goes to the write back stage, the ALU out value can be written into the destination register and so on. Right? The only important thing to be done in order for us to fetch instructions in every cycle is that we need to update the program counter, and the next program counter value has to be written back into the PC so that we could go and fetch the next instruction. Therefore, what you can see here is that there is some kind of, we are going to see this circuit even in a more optimized form a little later on. But as you can see here, you see that the value of the next program counter, sorry, there is, yeah, okay. So you can see here, the multiplexer has been moved into the instruction fetch stage rather than from here. And what happens is that once you compute the next program counter value, that value immediately goes back into the program counter in the next cycle, so that you could fetch the next instruction in the following cycle. Of course, when you have a branch instruction, it is going to create some problem. We will talk about that subsequently, and we will say how that can be handled. But if the instruction is not a branch instruction, then of course the PC plus 4 is what has to go to the program counter in order for you to fetch, and that path is shown by these blue lines, which is correct. Okay, so we will worry about branch instructions little later. Other than that, this pipeline that you see here is exactly same as what you saw in the case of the processor data path, except that there are some additional buffers which are included to implement the buffer. Okay, so looks like I'm going a little bit slow, maybe about 10 minutes slower. Hopefully I should be able to catch up in the next lecture. Should we go ahead and continue? Because I'm already late, I don't want to delay it further, right? Technically, there is no break between the previous lecture and the next one.
Yes, sir, we can go ahead.
The recording is continuing, I believe.
Yes, yes.
Okay. So let's now talk about pipeline hazards. So what I said is that you get a throughput of one instruction every cycle in the case of an ideal pipeline, but ideal pipeline does not happen. There are hazards which are encountered. These hazards can be either structural hazards, right, data hazards, or control hazards. I'm going to explain each one of them in the following slides. So let me not spend time here, right, and go to the next set of slides and then talk about each one of these hazards in some level of detail. Okay, so structural hazards happen. Let me just see. Okay, so structural hazards happen because, right, two instructions, right, two or more instructions rather, right, are trying to use the same resource at the game time, right, maybe from two different stages. Then a structural hazard can happen. So let me try to give you an example of this, right, with the following way, right. Let's assume that my memory has a single port and it is the same memory for both instruction and data, right. And we know that in the case of the instruction fetch stage, right, the memory is accessed to get the instruction. And in the case of a load store instruction, the memory is again accessed for performing the load or store operation. If the ith instruction is a load instruction, right, then in the instruction fetch stage, it will access the memory, and also in the memory stage also it will access the memory because it has to perform a load operation. Now let's see what happens when I pipeline successive instructions into the processor. The I plus 1th instruction starts one cycle later, and the I plus 2nd instruction starts one more cycle later. Okay, so that starts in time t plus 2. Okay, and then when you come to the I plus 3rd instruction, right, the I plus 3rd instruction has to perform instruction fetch, and at the same time that the ith instruction has to perform the load operation. And if I have only one memory port available in the processor, then both of them are going to compete for that single memory port, right? So this is what is called a structural hazard. Obviously, only one of them should be allowed to go, the other one has to be stalled. And in this case, if you allow the ith instruction to proceed and stalling the I plus 1th instruction, right, the I plus 3rd instruction, the I plus 3rd instruction will not complete in the cycle following this. It may take one more extra cycle because in this cycle it doesn't process the instruction fetch. It has to do the instruction fetch in the subsequent cycle. So you can see that there is a bubble that is coming out. So you can see that, you know, in cycle t plus 4, t plus 5, t plus 6 instructions are completing, whereas in cycle t plus 7 there is no instruction which is completing, but there is a bubble. And then of course in the cycle t plus 8, right, there is an instruction which is complete. This is what is called the structural hazard. The simplest way to avoid structural hazard is to provide additional resources. In this case, provide an additional memory port. Therefore, both, you know, the instruction fetch stage and the memory stage can access them independently, which is what happens in normal process. Okay, that is structural hazard. Next, let's talk about data dependency and hazards due to data dependency. Before we talk about data hazards, let me just explain all the data dependencies. So the data dependencies are classified into three things. One is called the true data dependence, or what is called the read after write dependence. Let me give you an example to illustrate this. Consider a sequence of instructions like this, right? Now you can see that the first instruction produces a value in R3, and that value R3 is being used in the second instruction, right? So this is what is called the true data dependence. Unless this first instruction completes its execution and writes a value into R3, the second instruction will not be able to use that value. So here, this read of R3 must happen after the write. So this is read after write dependency, right? that is written as a raw dependency, which is what is called a true dependency. There are also two other dependencies, one called the anti-dependency and the other one called the output dependency, respectively called as var dependency and var dependency. And the same example has these also illustrated here. Between the second and third instruction, right, the R3 register is being reused. Right? Here what happens is that you have used the value of R3, did some load, and then you are now writing something into your R3 register. There is of course another true dependency from this R3 to R3. That is fine, right? But then between this R3 and this R3, there is a dependency which is called the var dependency or the write after read dependency. What this says is that this instruction should not write the value into R3 until this instruction reads the value, because if this overwrites into R3, then this cannot read the old value of R3, which is required for performing the load operation. That is why this var dependency is important. Right? Of course, this var dependency would not have been there if I have used some other register like R9 or R12 or whatever it is. Correct? This dependency came because I was just reusing the same register. Right? If I have used some other register R12 here, this dependency would not have come. Whereas I cannot say the same thing about this register, because if I have renamed this register into, let's say, R12 or R15, then I have to use the same register R12 or R15 here in order to keep the raw dependency, in order to keep the semantics of the computation. That is why this dependency is called true dependency, whereas these two dependencies are called false dependencies. They are introduced because we are reusing the same register. The last dependency, which is a write after write dependency, is between the first and third instruction. And again, you have to understand here, the third instruction can only start its execution or only start writing the value into the R3 register after the first one has completed. Because if the third instruction does the write first and then the first instruction does the write to R3, then of course the new value of R3 is overwritten by a older value. So that is why this dependency is called a var dependency. In the case of a simple 5-stage pipeline, only the raw dependencies can happen. And if the raw dependencies happen, it can actually delay the pipeline execution. We will see that, and we will see that as the data hazards. Okay. So here is an example. Let's say that the ith instruction is an add instruction producing a value into R3 register. And let's say the I plus 1th instruction uses that value of R3. If you do not have pipelined execution, then of course the ith instruction would complete its execution, have the value written in the R3 register in the write back stage, and then the I plus 1th instruction can start its execution starting from IF and so on. Whereas now what happens is that the I plus 1th instruction starts its instruction fetch one cycle later, and it actually goes into the instruction decode stage when it expects to read the value of R3. But the value of R3 is written into this register, or the result of this add instruction is written into the R3 only during the write back stage. Therefore, what you are trying to do is that you are trying to read a value 2 cycles before it is actually written into the R3 register. Right? So if you are implementing this in the pipeline, then the pipeline has to detect that there is a dependency between the previous instruction and the current instruction, and it has to stall the execution of the current instruction. So that means that it creates bubble in the pipeline. Right? Even in the next cycle, you can't execute because the value is not going to be available in cycle 3 either. Right? So once again, you create bubbles. And then let us say in the next cycle, right, assuming that you do certain hardware optimizations where the write happens during the first half of the write back and the read happens in the ID stage during the second half, then possibly you can execute this instruction. So in this case, because of this data dependency, there are 2 stall cycles which were created. That means that in the pipeline executions, there are two bubbles that were created, which is going to cause increase in the cycles per instruction. That is, you are not going to get the ideal CPI of one instruction every cycle. Okay. Now, of course, the very first thing that you have to do when you implement pipelining is that whenever there are dependencies, if there are no mechanisms for handle this dependency, you have to stall the pipeline, like what we saw in the previous slide. Of course, you can also do what is called pipeline bypassing or pipeline forwarding, right, to avoid some of these stalls. And let me just give you an example of this in the next slide. Okay, so once again, let's take the same set of instructions, right, and look at it in the following, right? So what we saw is that the second instruction is trying to read the value of R3 from the register file. And of course, the value is not going to be available in the register file, and therefore it has to be stalled. But the question is the value not available in the register file, or is the value not available at all when you want to perform the execution of the subtract instruction? Right? The value of R3 was actually computed by the previous instruction in the EX stage. Therefore, at the end of the EX stage, the value of R3 is already available, perhaps in the ALU out register. Right? Only thing is it took 2 more cycles for it to be written into the R3 register, but the value that was computed is already available over here. Therefore, right, if instead of trying to read the value from the R3 register, if you can actually bypass the value from the ALU out register directly to the EX stage, then you can in fact execute the subtract instruction without any delay. Right? You don't try to read the value from R3 during the decode stage, but bypass the value from the EX stage. Supposing, let's say that the I plus second instruction is also dependent on R3. Then also we can actually bypass the value, right? Because again, don't try to read it in the ID stage because it's not going to be available. It's going to be written only in the next cycle. So you can actually read it from the ALU out stage, right? But there is a small difference here because by the time that this instruction goes to the EX stage, this instruction would have moved to the memory stage. Therefore, this ALU out register would have been copied from here to here. Therefore, instead of doing this bypass, you will do this bypass, right? From the ALU out register from the between the memory and write back stage of that instruction. Okay, so by doing this pipeline forwarding or bypassing, the data hazards can be taken care of, right? Okay, so this is the hardware circuit that is required for taking care of bypassing. As I said, you take the value either from the ALU out and give it as the operand. It can either be the first source operand or the second source operand, or you take it one cycle later and you can give it either as the first source operand or the second source operand, or it could come from memory. Okay, we will talk about this in the next slide, and you could forward it to as either the first source operand or the second source operand. Of course, now your multiplexers take one of these inputs and then choose the right one to be fed to the ALU. So the pipeline forwarding is essentially taking values not just from the register, but from this ALU out register, which is either between the EX and MEM stage or between the MEM and write back stage. Okay, now we talked about the load instruction and the value being written, right, in the LMD out register. Let's see what happens if the load instruction and the subsequent instructions are dependent on each other. Let's say the ith instruction is a load instruction and the I plus 1th instruction is dependent on the load instruction. Right, again, you can see that there is a true dependency from R3 to here. Okay, now what happens here is that in this case, the value of R3 or the value which is loaded from the memory is going to be available only at the end of the MEM stage. Therefore, if you try to forward this value to the EX stage, it's not possible because the value itself is going to be available at the end of this cycle, and you can't obviously get it at the beginning of this cycle to perform the subtract operation. So in this case, you have no option but to delay the execution. And only in the next cycle you can do the forwarding, and the subtract instruction can continue this execution. So if the ith instruction is a load instruction and the I+1th instruction is dependent on that load, then you can't avoid the pipeline stall. You have to at least incur one stall cycle. In general, if the execution takes multiple clock cycles, we will see an example of how that could happen a little later on, then if there are multiple cycles that are required for the execution, then not all of them can be bypassed. Only some of them can be bypassed, So in this case, you can actually think of the load operation being executed both in the EX and MEM stage. That is why it is two stages, and only one of those stages can be, one of those stalls can be bypassed, the other one cannot, So in cases of deep pipelines, this is going to be an issue. That's something that you need to remember. Okay. Of course, what one can do is that if you have instructions, you can actually reorder instructions as long as the semantics of this is preserved and all the data dependencies are preserved. I will talk about static instruction scheduling little later on, So I will skip the details for now and then come back to this later. Okay. We'll also talk about dynamic instruction scheduling, which will set the stage for out-of-order execution. Okay. Now, let me quickly go on to control hazards. Okay, the third type of hazard is control hazard. What happens if the ith instruction is a branch instruction or a unconditional jump instruction, if it is a branch instruction, let's assume that the condition evaluation and target address calculations are being performed in the EX stage. Now, in the next cycle, should we fetch the I+1th instruction or should we fetch the instruction from the target location? In fact, when you go to the next cycle, you won't even know that the previous instruction is a branch instruction. Only after you do decoding of the previous instruction, you will realize that this is a branch instruction, So obviously here, since this is a branch instruction and you wouldn't know whether the condition is true or not and what the target address is, you can't do any instruction fetch at this point in time. So you have to create pipeline bubbles. The same thing also happens in the next cycle. If the condition is evaluated at the end of the EX cycle and the target location is available, then perhaps in the next cycle, the instruction either from I+1 or from the target location can be fetched. Therefore, whenever you have a conditional instruction execution, you will incur at least 2 pipeline stalls in the case of the simple 5-stage pipeline. And of course, here is the hardware to implement this in a more aggressive way, where you try to do this condition evaluation as well as the target address calculation. Also in the instruction decode stage, there is some aggressive hardware implementation. Let me not go into the details. But even if you do this during the instruction decode stage, all that you can do is to reduce this 2 stall cycle to 1 stall cycle, but still you will incur 1 stall cycle because in the next cycle you wouldn't even know whether the previous instruction is a branch instruction or not and whether it is going to jump to the target location or not, So that is the difficulty. So with every conditional branch instruction, conditional or unconditional branch instruction, you will at least incur 1 stall cycle, Okay, so now let us see mechanisms for avoiding the stall cycles because of branches. Of course, what we can do is that we can have a static branch prediction policy, And this static branch prediction policy can simply say that every instruction, even if it is a branch instruction, is not going to take the branch. That means that the outcome of the branch is that it's not taken and the next instruction is going to be executed. If you pretend that this is your prediction policy, then what you can do is that in every cycle you can actually go and fetch the next instruction, that is from PC plus 4. And whenever the prediction is correct, right, you have done the right thing because the prediction is correct, which means that the branch is not taken. You have already fetched the instruction from PC plus 4 and you can go ahead and execute the instruction. So in those cases, the stalls would not have been income. Right? So this is one policy, which is what is called the static not taken policy, where you assume that the branch is not taken. Therefore, in the next cycle, you go ahead and fetch PC plus 4 and start executing. Of course, if the prediction is wrong, then you have to squash whatever that has been fetched and start fetching from the correct location. Right? A simple static taken policy will not work because you don't know the target address, so you don't know where to fetch from. Even if you assume that it is taken, you don't know where to fetch from. Therefore, a static taken policy is not good, whereas a static not taken policy is easy to implement. Okay, there are also other simpler approaches like what is called delayed branching, which is often implemented in many of the RISC processors. And the idea here is that if you have only one stall cycle that is needed to be taken care of, then of course what you can do is that after the branch instruction, you can put a no op. And then you can predict that this is a not taken policy and then go and fetch the next instruction, which is a no op instruction. Right? But that wouldn't really make any difference because no op is essentially executing nothing. Even though you have not incurred a stall, you have executed a wasteful instruction. But then what delayed branching does is that it essentially says that instead of the branch taking place immediately after the branch instruction, it takes effect only after the next instruction. That means that irrespective of whether the condition is true or not, irrespective of whether it is a branch instruction or not, the next instruction, the instruction following the branch instruction, is always executed. And then, of course, if the branch is a conditional branch, then the subsequent instruction is executed only if the branch is not taken, otherwise it goes to the target location. Right? So let us say if a processor implements what is called this delayed branching, then the slot next to the branch instruction is what is called the delay slot. And you can actually move some useful instructions. In this case, for example, the add instruction on which the branch is not dependent on can be moved from this delay slot down to, from the position above the branch into the delay slot. And for example, the branch instruction is executed. After that, the add instruction will be executed irrespective of the branch outcome. And then, of course, after one cycle, the branch outcome is known, and you can know whether to go to the target location or the next program counter and start executing this instruction. This is a simple trick that many processors implement, and it is available. So if you compile your program with and without optimizations, you will see that there are these no op instructions which are coming after each branch instructions, right, in the case of an unoptimized compilation, whereas in the case of an optimized compilation, many of these no ops will actually be filled with instructions which are typically as a part of the instructions which are before the branch instructions or whatever. How exactly the compiler fills it, there are lots of details, but I'm going to skip that, which is actually specified in this slide, but I'm going to skip that in the interest of time. Okay, well, delayed branching is one aspect which is not which is important and is actually done by the processors, but there are more things which are being done by the processors which are a lot more exciting, and let's look at that. And that gets us to what is called the branch prediction. Okay. Okay, so far what we saw is that we have the static policy, right, that we saw as a static branch prediction policy, which is the not taken policy, where uniformly across all branches, you take the same policy, which is not taken. Whereas in the case of a dynamic branch prediction, what you do is that for different branch instructions, you employ different prediction policies. Not only that, even for the same static branch instructions, each time that you execute, you may predict differently, right? For example, let us say that there is a branch instruction inside a loop. That branch instruction might be executed 1,000 times. Each time when you come to that branch instruction, the branch predictor may predict a different outcome. And depending on that outcome, it may behave differently, right? That is what is called a dynamic branch prediction. Dynamic branch prediction, right? So there are different kinds of branch predictors. One called the 1-bit predictor, the 2-bit predictor, then there are 2-level predictors, there are path-based predictors, and so on and so forth. We will see some examples of 1-bit, 2-bit predictors as well as 2-level predictors in this lecture, right? Okay, so one simple way to predict a branch is to kind of see what happened the last time when you encountered this branch, right? And then simply say that if the last time when you encountered this branch, if the branch is taken, assume that the policy is taken. Last time when you executed, if the branch was not taken, let's assume that the branch is not taken. So just imitate whatever that happened in the previous instance of this branch, right? So that can be implemented using a simple branch prediction buffer, right, which stores 1 bit of information which said what happened the last time. So you use the program counter, which is the program counter of the branch instruction, index into this buffer location, find out if this location is filled with some value, what that value is. If that value is 0, it means that it was not taken last time. So let's predict it as not taken. If the value is 1, let's say that it was taken last time, so let's predict as taken. And then after the branch is executed, right, whatever is the outcome of the branch, you update it so that you know that for the next time when you execute, you know what happened in the current iteration, right? So this is a simple 1-bit branch predictor, right? And the branch prediction buffer is of some fixed size. It could be something like 1K entry or 2K entries. And the program counter, some bits of the program counters are used to index into this entry. So for example, if it is at 2048 entries, then some 11 bits of the program counters are used to index into this. So the least significant 11 bits, leaving out bit 0 and bit 1, could be used to index into the branch prediction buffer. And that gives you the outcome of the branch, right? Okay. Of course, since you have only a limited number of entries in the branch prediction buffer, it is possible that 2 different branches at 2 different locations in the program may have their program counter values such that the 11 bits that you use to index are identical in those 2 branches. In which case, one branch is going to actually predict based on the outcome of some other, may possibly predict based on the outcome of the other branch. This is what we call as aliasing, because these 2 branches, these 2 static branches in the program, they have their program counter addresses such that those 11 bits that you are going to index, use for indexing into the branch prediction buffer, are identical. Therefore, one might be influenced by the other. Of course, you can't do much about it, and you let that happen in the sense that, okay, I mean, it's better than not predicting, therefore you might as well predict using the influence on the other branch. Okay. All right. Now let's extend this for a 2-bit branch predictor. Okay. See, the problem with the 1-bit branch predictor is that it is not very stable, right? It will toggle every time you make a wrong prediction, right? And it will easily go to the other state. And this therefore incurs more mispredictions. Instead of that, you do something like a 2-bit predictor, where the branch predictor would behave in the following way. It will initially be in one of these states. Actually, it is implemented as a state transition diagram or a state machine. It's initially in one of these states. Let's assume it is initially in the strongly taken state. So in this state, it will predict as taken. Okay, and as long as the prediction is correct, it will continue to be in the strongly taken state. If the prediction is wrong, it will move from the strongly taken state to the weakly taken state. See, if the prediction is wrong, that means that the branch outcome was not taken. Then it goes from this state to a weakly taken state. But even in the weakly taken state, the prediction is still taken, right? But only thing is that it is not very confident about it, right? That's why it is weakly taken. So in that particular state, if the prediction is again wrong, that means if it is a not taken resolution, then the branch predictor changes its prediction policy from a weakly taken to a strongly not taken policy, not taken state, right? But when it is in the weakly taken state, if the prediction turns out to be correct, then it goes back to the strongly taken state. Similarly, when it is in the strongly not taken state, whenever the prediction is correct, it continues to be in the strongly not taken state. If the prediction is wrong, it goes to the weakly not taken state. If it makes two wrong predictions consecutively, then it goes back to the strongly taken state. But if after one wrong prediction, if the prediction is correct again, it comes back to the strongly not taken state. So in this case, what happens is that there is something called a hysteresis that is being built in. That means that you have to make two wrong predictions before you could switch the policy. Right? This often works better in predicting branches. Okay, so this is implemented using a 2-bit predictor. There are different ways in which you can actually implement this 2-bit branch predictor on the state machine. This is one particular way. Okay, and it is implemented. It could be implemented using saturating counters. And in the case of programs, it gives a very good prediction accuracy, somewhere between 85 to 90%. Okay, so this is how the 2-bit predictor works. Again, you have something like 2K or 4K entries, which are indexed using some bits of the program counter. And this now, instead of containing 1 bit of information, contains 2 bits of information. The most significant bit tells you whether it is a taken or a not taken prediction, right? And the other bit essentially tells you whether it is strongly or weakly correlated, okay, or strongly or weakly taken states, or weakly not taken states. And after each branch resolution, you update the bits based on the state machine, right? Okay, now let's take an example of a nested branch. Right, so here we have two loops, L1 and L2. Right, L2 is nested inside L1. So let's say that there is a branch which is going right from B1 to L2, and there is a branch which is going from B2 to L1. Now you can see that for this particular branch instruction, if you used only a 1-bit predictor, then initially the branch will be predicted wrongly. And at the end of the loop again, the branch will be predicted wrongly. And again, in the next iteration, when it comes back, it will predict wrongly because it was supposed to go back, right? So in this case, a 1-bit predictor would actually make 2 wrong predictions. Whereas a 2-bit predictor, right, it will only make 1 wrong prediction at the end of the iteration, but it will go from, let's say, a strongly taken to a weakly taken state. And the next time when it comes to the same branch instruction, it will predict as taken, and that prediction would be correct. So it will actually move back to a strongly taken state. This is where the hysteresis really helps. Okay. But so far what we have talked about is that we have talked about how to find or how to predict whether the branch is taken or not taken. We haven't really figured out whether what the target address is. See, this is one of the problems, because if you say that the branch is predicted as taken, you also need to know what is the target location. To predict the target location, we maintain a separate buffer called the branch target buffer, right? The branch target buffer has an organization something like this. Again, this is a set of locations, maybe something like 1024 or 2048 locations, right? And again, indexed using the program counter. Some bits of the program counter are used to index into this. And each one of these locations now contains the target address of the branch. Right, the last time when the branch was executed, the target address would have been calculated. That target address is actually stored in the branch target buffer. So every time when you execute this particular static branch instruction, the target location wouldn't change because it is a fixed offset. Remember that, right? The offset is a constant. The program counter value is also the same for the same static branch. So the target address location is always the same. Therefore, whenever you execute this particular static branch instruction, this is the target location, right? So after you have seen this, if you have seen the branch once, then the target location would be available in the branch target buffer. So the next time when you execute this branch, using the program counter bits, you can index into the branch target buffer and you can get the target address. In fact, you can get the target address as soon as you have the program counter value. You don't even have to decode the instruction to understand that it is a branch instruction, right? Like what we said in the case of the branch prediction buffer, even in the branch target buffer, you could have aliasing of two different static branches. That is, two different static branches mapping to the same location in the branch target buffer. In the case of prediction, it is okay because there you are only predicting as taken or not taken, and any aliasing there wouldn't really matter. Whereas in the case of a target location, if there is an aliasing, then what happens is that instead of going to the correct target location, you will go to a wrong target location, which is actually not very good. Therefore, you try to distinguish that by means of this tag bit. So the tag bit essentially compares, right? If there are two static branches which map to the same location, the tag bits would be different for them. So in that case, you will say that although I have an entry in the branch target buffer, that entry does not correspond to this particular PC. Therefore, I can't use this target address. So that is what is this target bit, this tag bit for. V stands for the valid bit. Okay, so the details are explained here in the slide, but I already described that to you, right? So I will not go through each one of those bullets. Okay, so the branch target buffer and the branch prediction buffer together help you to identify A, the prediction, and B, the target location. And in fact, now if you see, you can actually do the prediction and the target location as soon as you have the value of the program counter, right? Therefore, the program counter is available in the IF stage itself. Therefore, in the IF stage itself, you can access the branch prediction buffer as well as the branch target buffer. And if you have a hit in the branch prediction buffer or in the branch target buffer, particularly in the branch target buffer, you know that this instruction is a branch instruction because only for branch instruction, you will store the target address in the branch target buffer, right? So if there is a hit in the branch target buffer, then you know that just by looking at the program counter value, you can say that this is a branch instruction whose target location is this. And the value that you get from the branch prediction buffer tells you whether the branch is likely to be taken or not taken. Then depending on that, in the next cycle, you can fetch instruction either from the I+1 location or from the target location, depending on the prediction, right? And after the branch is executed, if the branch resolution happens to be correct, then you are fine, you have not incurred any stall cycles. But if your branch prediction turns out to be wrong, right, then of course whatever instructions you have fetched them speculatively, therefore you have to discard it. And you have to update your branch prediction buffer. Branch target buffer need not have to be updated because the target address is always going to be the same. Right? So this is how branch prediction works. Any quick questions on branch prediction before we go to some other advanced branch prediction methods?
Sir, good morning. I have a small question. Let's say there is a branch that was never seen by the predictor before.
Correct.
And we now have that branch being taken. So what is the policy that's initially being assigned?
So what is going to happen when you index into the branch target buffer?
What I'm trying to ask is, would it be weakly not taken or would it be strongly taken?
Okay, so initial value for the prediction could be anything, right? See, again,
Okay.
Don't worry about what happens the very first time, right? You are not worried about what happens initially. You are only worried about the steady state.
Okay.
Right?
Yeah.
So that shouldn't really worry. I mean, if you're going to execute the branch 1,000 times, right?
Yeah.
The first few times doesn't really matter. First 2-3 times doesn't really matter. What happens the remaining 997 times is what matters, isn't it?
Right.
Okay. Okay. Now let's quickly see some other branch prediction schemes. One of the prediction schemes is actually not to predict individual branches, but to predict a path altogether. For example, here you could see that there are two conditional branches which are predicted together by predicting this path. I will not talk about a path prediction scheme in this lecture, but one can actually look into the literature to find out about these path prediction schemes. But we will talk a little bit about these correlated predictors, right? And here it's an interesting thing that happens. If branch A is not taken, then branch D is always taken. Let's say that we have a sequence of instructions which behave in this way. That means that this path, right, is always the right path. I mean, if this branch is not taken, then it only goes this way. If the branch is taken, either it might go this way or it might go that way. May be possible, right? You have situations like this in programs. And when you have situations like this, trying to predict D independent of A may not be very successful because D after all depends on A, right? Do we have situations like this in real code? The answer is yes. For example, here is a sequence of code which says that if AA is equal to 2, then set AA to 0. If BB is not equal to 2, set BB to 0. Then, of course, there is a condition which basically says whether AA is 0 or BB is 0, do something. Now, if I try to write this down in terms of the conditions, right, if I look at the history of branch 1 and branch 2, this is branch 1, this is branch 2, if either branch 1 is taken or branch 2 is taken, then they are going to set the value of AA to 0 or BB to 0. And branch 3 is essentially checking whether either AA is 0 or BB is 0. Therefore, you could see that if branch 1 is taken, right, or if branch 2 is taken, if either one of those branches are taken, or even if both of them are taken, AA is going to be 0 or BB is going to be 0, or both are going to be 0, in which case branch 3 is always taken. Correct? Whereas if neither of these branches are taken, then I don't know what would be the value of AA or BB, so I can't really say anything about branch 3. But then in all these other 3 cases, I can definitely say that the branch 3 is going to be taken. So can I capture this information in some sense and make use of it? Okay, so if I look at it in terms of branch history, right, if the two branches, branch 1 and branch 2, they are both taken 1, 1, then branch 3 is always taken. If one of them is taken, the other one is not taken, or the first one is not taken and the second one is taken, then also branch 3 is going to be taken. To capture this, what we do is that we have what is called a branch history register, which captures the outcome of the last k branches. In this case, k was 2, right? So if the branch is taken, you push a 1. If the branch is not taken, you push a 0. So you keep pushing these values into the branch history register, which stores the information about the last k branches. Okay, the dynamic last k branches. In this case, we are talking about branch 1 and branch 2. Right? If this had a value 1, 1, then it will go and index into a location which corresponds to 1, 1. If it had a value 1, 0 or 0, 1, it will go and index into that particular location. Correct? And that location again will actually store the pattern of what happened in the last few times when that pattern was seen, right? So after an initial few attempts, you're going to see that for these branch histories, right, the branch is always taken. So it's going to capture the taken policy. So it's going to capture it in terms of strongly taken or weakly taken policy, which after some time would stabilize to strongly taken. So the pattern is actually captured by the branch history register. And what happened in the previous time when this pattern was seen is captured in this pattern history table, right? So the last k dynamic branches are stored in the branch history register. And what happened when that particular pattern of branch history was seen is stored in this pattern history table. Okay, again, there are different schemes. I have a lot of details in this, which I'm going to skip in the interest of time. So in this particular case, what is called, is there a question there or somebody has not muted their mic? Okay, so in this particular case, what we have is that we have a global branch history register and what is called a global pattern history register. There is only one branch history register and one pattern history table, right? As opposed to this, you could have one branch history register and multiple pattern history tables, right? You use the branch history register depending on whatever is the pattern, index into a set of pattern history tables, and then you choose one of those pattern history tables based on your program counter value. So this particular scheme is what is called the global branch history register per address pattern history table, because that is based on the PC value. You could also have something which is per address on both cases. You have a per address branch history table. It's no longer a single register, it's a branch history table, because for each PC value there is a separate branch history register. And that stores the pattern of the last k branches. Then from there you index into a set of pattern history tables, right? And in that pattern history table, you pick one of them based on the program counter value. So this is what is called a PAP scheme, per address branch history and per address pattern history. Whereas the one that we saw in the previous slide, this one is basically global branch history and per address pattern history. And the first one that we saw is global branch history and global pattern history. You can also have the other way around, per address branch history and global pattern table. That is also possible, where you have only one pattern history table. Okay, there are also other variations which they talk about in the literature. Let me not go into that. Now, let me talk about this one special predictor, which is what is called the G-sharp predictor. I'll simply explain this with the help of this diagram. Right, this is similar to the GAG predictor, but except instead of just using the branch history register value, you XOR it with the program counter value to give some flavor of the static branch instruction, because different static branch instructions which point or which see the same branch history, if you want to predict them differently, then what you do is that you use a combination of the program counter value and the branch history register. That's essentially what this G-sharp predictor is. Of course, when you talk about these two-level predictors, right? The two-level predictors has possibly multiple branch history registers and then multiple pattern history registers, and the amount of storage that they might require could be quite large. And it's not just the storage, but these predictors will start behaving correctly only when all of these bits are filled in, or only when you have seen all of these patterns and you have seen how the branches are behaving, right? But if in the meantime, if there are frequent context switches that are happening into the program, then of course these branch histories are going to be flushed. That makes these particular branch predictors not performing well. So this results to poor prediction accuracy during context switches. So people also tend to use what are called hybrid predictors, where you use not just one predictor but multiple predictors. Let me give you one simple example in the next slide. Again, I will not go into all the details because it may take time to go through. So let me just quickly go to the diagram and show you what's happening there. So let's think of the first predictor, which is a GAG predictor, right, which is basically using a branch history register and a global pattern history table, and it predicts using that. This is one predictor. There could be another predictor, which is a PIG predictor, which has per address branch history and a global pattern history, right? So in this particular case, we are talking about two predictors, and both predictors are allowed to make a prediction, right? And then, of course, you have what is called a meta predictor, which predicts which one of these two predictors should be used, right? That meta predictor is over here. Then depending on what the meta predictor chooses, you choose that particular prediction and then apply. So for example, let us say in this case, this requires a lot of history to build up this table. So this predictor may take a longer time to warm up. And until that time, this predictor might be used for predicting. But once this predictor has warmed up and has most of the entries filled in, then this predictor would start predicting more accurately. Then you will start predicting from this predictor rather than from the other predictor. You could in turn think of something like 3 or 4 predictors for a particular thing, right? These are called the tournament predictors, and this was first implemented in the DEC Alpha 21264 processor, at least proposed in the DEC Alpha 21264 processor, right? So one can think of more complex branch predictors, right? So we saw simple 1-bit predictor, 2-bit predictors, and also what are called the correlated predictors, right, where one branch determines the prediction outcome of another branch and so on. Okay, so that kind of completes our discussions on branches. There is also some discussion on indirect branches. So far what we saw were simple branches where the rate offset was specified as a part of the instruction. But there are other kinds of branches which are called indirect branches, where the offset could be either in some register, not the offset, the target location could be in some register, because for example, in the MIPS architecture, you have what is called a jump register instruction, where the target location could be in a register, right? Or you have simple function returns or procedure returns, right? Where you return not just to a specific location, but from the location from where the function was called. In these cases, identifying the target location is difficult. So you need to have special mechanisms for identifying the target location. These are called indirect branches, where the target location, even though it is the same return instruction that you are executing, depending on where from this function is called, it returns to different locations, right? Similarly, when you're trying to implement a switch statement in C, right, it is going to be implemented based on some conditional registers and jumps and so on. That also is going to be, even though it is the same static branch instruction, the location to which it can jump to depends on the register values, right? They are going to be complex. So these are called indirect branches, and there are special mechanisms for handling indirect branches. Again, we will just leave that discussion there and move on. Okay, now I'm going to go to the last part where I at least want to spend about 15-20 minutes of time talking about it. So before that, if there are any quick questions on branch prediction, maybe we can take that. Again, remember that when you do branch prediction, you are speculatively fetching instruction from one direction and start executing them. That speculation may be correct, may be wrong. But when the branch is actually executed, right, you find out whether your speculation is right or wrong. If the speculation is right, you simply proceed without having to do anything. But if the speculation is wrong, then the speculatively fetched instructions are squashed. And then the processor starts fetching from the correct location. Okay? Any questions?
Sir, is there any benchmark program which decides the predictor accuracy? Because as I can see, in global case, the accuracy will vary, right, for every application?
Right. Well, any predictor, right? Its performance will vary depending on the application. But then what you see is that many of these predictors which are designed tend to give a very high accuracy. Something like, for example, the 2-bit predictor gives you an accuracy between 85 to 90% or 95%, right? And on top of that, these 2-level predictors try to improve things even further. And then hybrid predictors try to achieve even more. There are standard benchmarks based on which they try to tune these predictors, how many bits to use, how many, what should be the size of the branch prediction buffer, and so on and so forth. And these are like commercial, these are standard scientific benchmarks like the spec benchmarks, or other benchmarks like TPC benchmarks, and so on and so forth. And they use actually multiple suites of benchmarks to tune these various parameters that they use to design the branch predictor. Did I answer your question?
Yes, sir.
Okay. Okay, let's do one thing. Let's complete our discussions on out-of-order execution. And then at the end of the lecture, again, we will try to stay back for some more time and answer questions. Right? Okay, so far what we have seen is that we have seen pipelined execution, where pipelined execution tries to achieve a CPI which is closer to 1. But all that we have tried so far is essentially trying to execute instructions, and then if the instruction causes certain dependencies which cannot be satisfied by bypassing or something, stall. Similarly, when you have a conditional branch instructions, if you are predicting and the prediction is okay, you are fine, but then if the prediction is wrong, you have incurring stalls and so on. But when you talk about instruction level parallelism processors, you are trying to fetch, see, in the case of simple pipeline, in every cycle you are fetching, decoding, or executing one instruction. Whereas in the case of ILP processors, you try to fetch multiple instructions in a single cycle. You try to decode multiple instructions in a single cycle, and so on. Right? And when you try to do that, you also have to see what happens when I am stalling because of a dependency. Should I stall this instruction as well as all other future instructions? Or should I allow some of them to start executing in some way so that I still make sure that all the semantics of my executions are maintained, but I try to execute instructions as early as possible? So that's essentially what we are going to see when we talk about instruction level parallelism and out of order issue and execution, right? But before we go into that, let's just try to look at a more realistic case of a pipelined processor execution, right? So far we saw only one pipeline, right, where we have the execute stage as being one single thing which can execute any operation. But that's a very unrealistic thing, right? For example, integer operations require a different kind of an ALU, whereas let's say a floating point addition or a floating point multiplication or a floating point divide requires different kinds of ALUs, right? And we also saw that instruction fetch takes the same amount of cycle as instruction decode, which takes the same amount of cycle as execute. But these are no longer true in realistic pipeline, right? For example, even in the very early MIPS R4000 processor, right, the instruction fetch took 2 cycles to complete, whereas the decode took only 1 cycle. So they divided the instruction fetch itself into 2 stages, one called the instruction fetch stage 1 and another called the instruction fetch stage 2. Similarly, memory was divided into 3 stages, okay, as you can see here. And then depending on the type of operation you perform, you either take 1 cycle or in some cases you take multiple cycles. In some cases, the functional unit itself is pipelined. In some cases, the functional unit is non-pipelined. For example, the divide is always not pipelined and so on. Therefore, more realistic pipelines essentially include multiple ALUs, right, depending on the type of operation to be performed. And when you have situations like this, it's quite possible that at the end of the execution, 2 or more instructions might end up in the write back stage together, and they may be competing for the write ports, write register file write ports, and so on. So they could cause additional structural hazards, right? It might also happen that one of the instructions, right, will be waiting on, let us say, a longer latency operation such as a multiply, and may be stalled, and because of that all subsequent instructions may be stalled, right? Those situations could happen. And let us say branch target address, right, might happen not just in 2 cycles but maybe in 3 cycles, because you have to go through IF, IS, then the decode stage, and then only during the next stage you will actually calculate the target location. So they may take more cycles, right? So branch stalls is 3 cycles in the case of the MIPS R10000 processor, because the target resolution happens only during the integer stage, right? And in certain cases, the true dependencies could be more than 1 cycle. For example, if a multiply instruction produces a value which is being used in the next instruction, the multiply instruction itself could take 4 cycles during execution, correct? And when it takes 4 cycles during execution, a simple bypass will not work. You will at least have to stall for 2 or 3 cycles before the bypass starts working, okay? Similarly, for the load instruction, it takes 3 cycles, right, between the load and the dependent instruction. Okay, and it may be possible that, you know, the ith instruction might still be executing. For example, the ith instruction could be a multiply operation, whereas the I plus 1th instruction is an integer operation which takes only 1 cycle and may complete its execution before the ith instruction completes its execution. So this is what is called the out of order completion of execution, right? That might happen. So what do we do in those cases? Right, in the case of a simple 5-stage pipeline, we saw that the var and var dependencies do not cause hazards, because, right, the writes always happen in a later stage, whereas the reads happen earlier. Whereas that may not necessarily be the case when you have more complex pipelines. So how do we handle those situations, right? Okay, so let's take some concrete examples and then see what happens. So here I have a divide operation followed by a subtract operation, which is dependent on the divide operation, whereas the third instruction, which is a multiply instruction, does not depend on the subtract or divide. So in this case, the subtract instruction is going to be stalled because it's expecting the result from the divide operation, the F4 register, and therefore has to be stalled, whereas the multiply instruction need not have to wait for it because it already has all the operands that it requires and it can possibly go for execution. So the question is, should we allow the multiply to go for execution, or should we stall because the subtract is stalled? In the case of out of order issue, the multiply is allowed to go and execute. Okay, that is what happens in the case of an out of order issue. Okay, so essentially we are going to reorder the instructions and execute them. And this reordering could be done statically at compile time, which is what is called the static instruction scheduling, or could be happening at runtime, which is what is called the dynamic instruction schedule. Right? And again, even in this dynamic instruction scheduling, you could either have in order or out of order instruction issue and execution. So we will talk about that in detail. Okay. And then you also talk about whether this completion also happens in order or out of order, right? Let me just go into the details for that real example. First, let's quickly talk about the static instruction scheduling. I will very quickly go through this. This is a simple for loop, and let's say that this simple for loop is, compiled into this set of instructions, right? Between the load instruction and the add instruction, there is a dependency, and this dependency requires 1 stall cycle. Let's say between this add instruction and the subsequent store instruction, there is a dependency of a 4 register, and let's say the floating point add takes 3 stall cycles. And of course, we'll also assume one branch stall cycle. So if you execute this instruction, because of these stalls, it might take, right, 11 cycles to complete the iteration. Because before this add can execute, there is one stall cycle. Before the store can execute, there are 3 stall cycles. So if you execute instructions in order, because of the stalls, it will take 11 cycles for it to complete. But if I reorder instructions in this way, where I move this integer add instruction between the load and add, and move this subtract instruction between the store and the floating point add, right? Then I can reduce some of these stalls. And of course, I can also remove the branch stalls by moving the store instruction to the delay slot, provided it implements delayed branching. Then I can actually execute this entire loop in 7 cycles, which is better than 11 cycles. Of course, if I unroll the loop 2 times and then I do the scheduling, right, where I have 2 copies of the load, add, and store instructions, right, and I do some rescheduling of this instruction, I can do it even faster, where I can complete each cycle in 4.5 cycles. Of course, the compiler is allowed to do this, and this is why your compiler have options to unroll the loop and then do scheduling. Okay, let's leave the static instruction scheduling there and move on to dynamic instruction scheduling. Right, in order for us to achieve this out-of-order execution, what we need to do is that we need to divide the instruction decode stage into multiple stages. One called the decode. The first part of it is called decode, where you decode the instructions and check for any structural hazards. Then after the instruction is decoded, it's actually dispatched into what is called an instruction queue or a reservation station. Right? At that point in time, up to this point, what you do is that you process the instructions in the program order. Right? You decode them in a program order, and then you dispatch them to the reservation stations in program order. Right? And in the reservation stations or in the instruction queue, right, it would be one of the 2 structures, it will wait for all the dependencies to be satisfied. And when the dependencies are satisfied, it moves from the instruction queue to the execution unit. And this action is what is called the issue. Okay, so it waits in the reservation station or instruction queue until all the data dependencies are resolved. Then once the data dependencies are resolved, it reads all the required input operands and then sent to the functional unit. So essentially, the decode stage that we saw earlier is split into 3 parts, where you do the decode and then you dispatch them into what is called an instruction queue or a reservation station. I will show the diagram in one of the future slides, right, that you will understand this better. And then it waits in the reservation station or instruction queue until all its dependencies are satisfied. When the dependencies are satisfied, it will read the operands and then move to the functional unit for execution. Then it executes in the functional unit, taking the required number of cycles. And after the execution is complete, it informs all the instructions which are dependent on it, saying that the result value is now available. Okay, so let's see how this happens. Okay, so the instructions, after they are fetched, they are put into the instruction buffer, from where they are actually decoded, right? And they are dispatched to what are called the reservation stations. So they are dispatched to the reservation stations here. There are separate reservation stations for each type of operation. For example, one of them is the integer reservation station. The other one is a floating point reservation station. This one is a load store reservation station, and so on. So after the instruction is decoded, it is dispatched based on whatever operation it is performing into the appropriate reservation station, right? And then it looks into the register. So the decode and dispatch stage also looks into the source operands. And if the source operands are available in the register file, they are also being read and stored in the reservation station. For example, let us say that in the example that we saw, the multiply instruction that we saw, go back a few slides, right? Or let us say the subtract instruction that we saw, the F4 operand was not available, but the F6 operand, it is not being prepared by any previous instruction. So maybe it is already available. So the operands which are already available, like the F6 operand here, can be read and put into the reservation station. Similarly, for the multiply instruction, right, both the F2 and F6 which are available can be read from the register file and put into the reservation station. Let me jump quickly to the slide. Okay. And those operands which are being executed by other functional units, right, they will be empty, they are not available. And there is enough indication in the register file saying that some functional unit is preparing this value. Therefore, those values are not read and they will be empty. But when the reservation station has all the operands available, then we know that that particular instruction is ready for execution and can be sent to the functional unit for execution. For example, here it is the integer functional unit, here it is the floating point functional unit. Similarly for the load store functional unit. So once the operation is executed in the functional unit, at the end of the execution, right, the value which is produced by the functional unit is broadcast to all the reservation stations. So for example, let us say the subtract instruction, right, the floating point subtract instruction, which is waiting for the divide, right, will be having its entry in the reservation station saying that one of its operand is available, the other one is being prepared by the floating point divide instruction. So when the floating point divide instruction finishes its execution, it broadcasts the value and saying that it is coming from the floating point divide, right? So that entry or that value can go into this waiting location. And when this entry has all the data operands available, that means that the subtract instruction is ready for execution. Then in that case, that the subtract instruction can be sent to the floating point functional unit in the next cycle or so on, right? Similarly, each one of these functional units, whenever their operations is complete, it is being broadcast to all the functional units, and the result value is also written into the register file. Okay. Okay, I actually described all of these things. Let me just go to the point about in order completion. So as you can see in the previous example, the multiply instruction, which is not dependent on the subtract or divide, can go ahead and execute its operation. Let us say if it completes its operation even before the subtract is completed, because it was issued out of order, right? Because you remember there was a divide instruction and then there is a subtract which was dependent on the divide. The subtract is waiting for the divide to complete, but then the multiply, which is after the subtract, can actually go for execution because all its input operands were available. It can in fact complete its execution and produce the result value. And it can even write the value into the destination location, right? This writing the value into the destination location and making that as available to all the future instructions, there is a process called the commit, which says that the instruction execution has completed its execution and is going to modify the architectural state of the machine, right? But in order for us to do that, we have to be careful, right? We can't arbitrarily, not arbitrarily, we can't just allow instructions to complete out of order for the following reasons. Okay, so let's look at the example over here. Okay, now let's say that there is a branch instruction, right? And this branch is speculated. Now, if the branch is speculated, and then let us say that this add instruction is executed, right? Let's say for some reason the branch took a lot of time to complete, but the add instruction completed its execution. Can it go ahead and change the value of R3? Because if it changed the value of R3, and then subsequently if you found that the branch instruction, right, was speculated wrongly, then this add instruction would have modified the contents of the R3 register, and then you have to say that no, this add instruction should not have been executed because it is a speculatively executed instruction. Its result should not have modified the R3 value. The architectural state should not have been modified because when I go to the target location, I need the value of R3, but that would have been wrongly modified by the speculated instruction. So in some sense, you should not allow, you can allow the add instruction to complete the execution, find the value, but if you write it into the R3 register, that modifies the architectural state, and you are doing it for a speculative instruction. If that speculation happens to be wrong, then the architectural state is inadvertently modified. Therefore, when you want to correct this wrong speculation and re-execute these instructions, you will end up into a problem. Correct? Similarly, right, let's look at one more case, right? If an earlier instruction generates an exception, right? For example, let us say that there is a divide instruction which is taking a long time to execute. Let's say that this add instruction has completed its execution, and here this add R5 essentially adds R5 to R4 register and puts the value back into R5. And let us say if this instruction is allowed to modify the R5 register, and then you keep executing a future instruction, and then at a later point in time you found that this divide instruction has caused an exception, then you're going to re-execute the divide instruction and then re-execute every instruction after that, then you find that the R5's value has already been modified, which is not correct, right? So for these reasons, right, you allow the instructions to execute out of order. You allow them to produce values out of order. The produced values can also be used by future instructions. But if they modify the architectural state of the machine inadvertently, then it would cause erroneous execution of the program. So while programs can be, while instructions can be issued and executed out of order, their completion or their commit into the destination register has to happen in program order. Okay. Okay. Now there is one more thing which is with regard to exceptions. Let me quickly talk about that. Is it okay if I take another 5-10 minutes to complete this, because you have a half an hour break? I will just eat about 10 minutes into that half an hour break. Okay. So let's think of two instructions of floating the multiply and divide instructions that you see here, right? If the divide instruction raises an exception, okay, first of all, that exception should be held until the divide instruction becomes, is ready to complete in program order. That means that all previous instructions have completed their executions and have committed that state. Then only the divide instruction would be allowed to raise the exception. Right? This is important because you don't want these exceptions to be raised, even particularly for a speculative instruction, and particularly if these instructions are going to raise exceptions in out of order. For example, let us say in this case both the divide and the multiply raise an exception, but let's say the multiply raises the exception first because it finished its execution faster. Then what happens is that the programmer would see the effect of the multiply instructions exception first and then the divide instructions exception, which is not the correct order. So processors have mechanisms for, when the instructions are executed out of order, their exceptions, when they raise exceptions, they are actually held and the exceptions were only handled in program order. So both the completion, that is commit, as well as the exceptions would be done always in program order. That is very important. Okay, let me just spend the last 2 minutes or 3 minutes trying to talk about the notion of a reorder buffer and why it is important. So in order for us to make sure that this commit kind of happens in program order, right? Remember that I said that for speculatively executed instructions, you don't want to go and affect the destination location. So what you do is that you introduce what is called a reorder buffer, right? This reorder buffer is a temporary location where the result value can be held. For example, for a speculatively executed instruction or for an instruction which is executed out of order, the result value is computed and is kept in the reorder buffer. The reorder buffer is something like a first in, first out buffer, right? And there is one location allocated for each instruction which is dispatched in program order. For every instruction which is dispatched, there is one location which is associated with this reorder buffer, right? And instructions are going to be committed exactly in the program order by just following the reorder buffer ordering. Because the reorder buffer is a first in, first out buffer, and one location is allocated for each dispatched instructions. Instructions are dispatched in program order, right? So for example, let's say if there is a branch instruction, then the branch instruction would have been given one location. There is a subsequent add instruction which is going to be executed speculatively. That add instruction will be the next location in the reorder buffer. The add instruction would not be allowed to commit until the branch instruction commits, because when the branch instruction commits, it knows that, right, whether the branch was predicted correctly or wrongly. If it is predicted correctly, then there is no problem. But if it is predicted wrongly, it will squash all subsequent instructions because they are speculatively fetched, executed, and so on. Correct? So now think of the same program that we saw earlier. There is a branch instruction and there is a speculatively executed instruction. The speculatively executed instruction would produce its result value, and instead of directly writing the result value into the register, it will now write the value into the reorder buffer in that particular location. So remember that our branch instruction, okay, let me take the pen here. So our branch instruction was allocated one location in the reorder buffer, okay, and the subsequent add instruction, which was speculatively executed, is assigned the next location. When the add instruction completes its execution, its result value would be written somewhere over here. I have to take a pen of a different color. Okay, so when the add instruction completes, that value would be written in the reorder buffer in this location. Any subsequent instruction which is dependent on the add would actually read the value from the reorder buffer. And any subsequent instruction which is dependent on the add, which is also executed speculatively. Correct? But only after the branch instruction completes its execution, the branch is first committed, and then subsequently the add instruction, when, right, if the branch is speculated correctly, then the add instruction would be committed. At that point in time, the value which is written in the reorder buffer will be written into the destination location in the appropriate place, right? By doing this, we are ensuring that the instructions are committing in program order and the architectural state of the machine is not modified. Okay, so I think the descriptions are over here. I have already explained this to you. Okay, with the help of this diagram. Okay, now you could also see that the reservation stations which try to read the value either from the register or from the reorder buffer acts as temporary locations, and they help to avoid any war and war hazards. There are some details that I am skipping here in the interest of time, but you can read about that to understand that. Okay, so I think I will more or less complete. So there is something about register renaming. I will not go into the detail for want of time, but I already explained to you with the help of the reorder buffer. Okay, so let me stop. There are only two more slides after that. So let me just introduce the notion of reorder, maybe just the notion of register renaming and stop that. Okay, so let's just look at what is in this slide. So as I mentioned earlier, right, true dependencies have to be satisfied, and you can't do anything about it. But false dependencies like anti-dependency and output dependencies happen because you are reusing the same register for some other location, right? So in this case, for example, there is a var dependence between the add and subtract instruction, right? And you could avoid this var dependence. And similarly, there is a var dependence between the multiply and divide instruction. You could avoid these var and var dependencies by assigning different registers for the subtract and divide instructions. So for example, if the subtract and divide are given different registers right at runtime, then what happens is that there is no dependency between the add and subtract, or there is no dependency between the multiply and divide. But what these different registers essentially mean is essentially different locations in the reorder buffer. And of course, each instruction is going to get a different location in the reorder buffer, and therefore they will all correspond to different registers. There are also other register renaming schemes, which Professor Arkaprabha Basu will talk about when he talks about superscalar processors. This process of dynamically giving a different register location or a register name is what is called the register renaming, right? Two different ways of doing the register renaming, one using the reorder buffer and the other one is using the physical registers. Unfortunately, we will not cover them in detail, but you can read about it either in some textbooks, right? Yeah, you can read about it in the Hennessy and Patterson textbook as well as Smriti's textbook. Okay, you can read about them. Okay, so here is basically a mechanism of how it is done. I will not go into the details for lack of time. Okay, so let me complete my lectures here. I will post all the slides in the Teams page. Let me take another 5 minutes or so if you have any questions, and then at least give you a 15 minutes break so that you could refresh yourself and come for the next lecture. So one or two quick questions if you have, I can answer.
Excuse me, sir.
Yeah.
Sir, I have two questions. So, why do we need a complete buffer for called reorder buffer? Like, why can't we just have separate bits to say whether it was generated out of order or in order?
Okay. Whether it is generated,
whether the value which is stored in the register is.
See, once you have a branch instruction and you speculate, all future instructions are going to be speculated, right? And roughly speaking, every fifth or sixth instruction in your program is a branch instruction. And if you're going to execute more than one instruction every cycle, right, every other cycle you are going to have a branch instruction. So majority of your instructions are going to be executed in a speculated way. And they are executed speculatively, but then as the branches resolve, the speculation is getting clear. So you do need them, and you do need them for multiple reasons, even for implementing things like exceptions properly. You do need them. It's not just enough only to tag speculatively instructions. In fact, many of the instructions are going to be speculatively executed. Okay, it's a short answer to your question.
Sir, sorry, sir, I got confused. So, if it is speculatively, like, if the speculation was correct, then that means our out of order execution was proper, right?
Correct. That is correct. No. See, whether the speculation is correct or wrong, until the branch is resolved, right? You don't want to modify the destination register, because once you modify the destination register, and after that, if you find that the speculation was wrong, then you have changed the architectural state, and therefore executing your program will not give you the correct result. So until the branch is resolved, you don't want to write into the destination location. The reorder buffer is essentially meant for holding the value until that time.
Yes.
Okay. And you can take it from me that many of the instructions, when they are executing, they're going to be executing, possibly executing as a speculatively executed instructions. Later on, they will be cleared, right? And they will probably write the value into the destination location.
Sir, I have one more doubt. Why do we need to consider register renaming? Because like the compiler can generate appropriate instructions, right?
Very good, very good. The compiler can generate, compiler can actually do register renaming to a large extent. Only thing is it can only do for a static part, right? So for example, right, when you have an if then else, at compile time you wouldn't know whether the then branch is going to be taken or the else branch is going to be taken, right? In those cases, the compiler based renaming wouldn't be very helpful. Right? And second thing is that the registers which are visible to the compiler is actually fewer than what is visible to the architecture. Right? And that essentially says that you have to do something more than what can be done by the compiler. All right?
Yes, sir. I got the idea.
Okay. Any other questions? See, I won't be available for the doubt clearing session today. For that matter, I'm not going to be available any of those sessions. So if you have any questions, you could ask me now, or yeah, you could ask somebody else who could also answer this reasonably well. They may not like doing it, but yeah, they're definitely competent enough to answer that. But if you don't have any question, that's also fine. We can stop here.
Thank you, sir.
Thank you.
Must be really late for you.
Yeah, but that's okay. If there are no questions, maybe we should give them 15 minutes time to take a break and come back, right?
There was some in the chat, was it?
Okay, let me just look at it if there are some quick things that I can answer, but let's just open it up. Oh. Okay, will branch target buffer be flushed at context switch? The short answer is yes, both the branch prediction buffer and the branch target buffer have to be flushed. Yeah, using address space ID is a way of using it, but typically I think it is not done. Let's answer. Okay. So somebody asked about this never seen branches, but answered that question. Okay, any algorithm associated with data path? I don't understand what that question is. Okay, so what was the question? This was asked by Shirley Miranda. Any algorithms associated with data path? Okay, if the person is not there, we don't have to worry. Again, I think the question with regard to branches which were not seen, what is the policy? Your initialization could be a weekly taken or a weekly not taken state. And then after one or two wrong branches, it will stabilize. So there shouldn't be a problem. Yeah, the branch target buffer and the branch prediction buffers typically are not saved during context switch. I am not very sure whether they use address space IDs. As far as I recall, they don't, right? Yeah, I think those are the questions, Madhura, that I could see in the chat.
Yeah, that's
that should take care of, right?
Yeah.
Okay.
Thank you.
Thank you. So see you next week then.
Yeah.
Bye.
Yeah.
Bye.
Bye. Thank you.
Bye.